Good morning. Welcome to the Rust project track at Rust Week. Thank you for coming. It's so great that you're here. I'm Adam. I'll be your MC for the day. I am on the Crates.io team in the Rust project. I'm really looking forward to this. I think this is going to be a great stream. There's a lot of awesome talks coming up. I can't wait to see all of them. All right, a few housekeeping things just before we get going. Organisers, as I'm sure you've all seen in the last day or so, are wearing yellow shirts. You can ask them when you need anything. My notes say anything, so random questions, they might be able to help you with those as well. But particularly if you have issues around accessibility or conduct or anything like that, please go talk to one of them. Speaking of, please follow the code of conduct at both at the main event and any related dinners, unconference, etc. You can find all those details on the website. Our agenda for today, there are, like yesterday, 3 tracks. There is the main track in Cinema 12, there is the deep dive track in Cinema 11, and this, the Rust project track in Cinema 9. We still have a couple of minutes before talks get going, so if you have accidentally found yourself in the wrong room, you have time to just sneak out and nobody will call you on it. Furthermore, you can also go meet the GoSim finalists downstairs on the mezzanine floor during the breaks. They would love to talk to you about their projects. And at the end of the day, there will be a social with drinks and socializing and conversations and all of those good things that you want to do at conferences. Anybody who wasn't here yesterday, who doesn't know about the Wi-Fi, the details are on the back of your badge. The password is extremely straightforward. I suspect you'll all figure it out. I've also, we also have the MakePad area, which is a mixed reality Rust programming thing, which sounds super interesting, which is in the event zone opposite Cinema 12. They would love to see all of you go check that out at the breaks again. And we also have the 10 Years of Rust celebration tomorrow, which tickets are available for. Some of you, I'm sure, already have tickets, but you can get tickets for that. That's going to be awesome. I'm told there is going to be some sort of, risky release behavior that I think will be pretty awesome. The pictures looked fun. Pietro is waving and doesn't look at all concerned about what's going to happen tomorrow, which is good. I, on the other hand, am on a team that's already been responsible for 1 outage this week, so, I really can't comment at this point. So, our very first speaker today has come all the way from New York, which used to be, of course, New Amsterdam. So I think we should just go back to that. And it is Michael Goulet, although most of you will probably know Michael better as compiler errors or just errs. Michael has opened over 2,000 PRs to the compiler in the last 4 years, which is impressive, terrifying. Good job. And he's going to talk about almost everything you should know about the compiler front end. And I'm going to fill for about 30 more seconds just for the online streamers because we're still not quite at 9:40. But I'm looking forward to this talk a lot. I know nothing about compiler front ends. This will be great.
Yeah, I guess, okay, my voice is on now. Maybe not starting just yet, but this is not a general introduction to the compiler, just warning you. This is mostly meant for people who've already kind of seen a little bit of stuff. So, my intention is to cache or to prime people's caches, to get people to hear at least about everything once. Then when you have to go back and revisit yourself, because a lot of working on the compiler is revisiting things yourself and learning things yourself, you'll at least have remembered at least vaguely where to look. Right, I guess it's 9:40, so
Perfect.
Should we begin?
Let's go. Let's give it up for Michael.
So this talk is a little informal. I'm going to be jumping through the compiler in the source code. I think this should be big enough. I'm going to be using these links down here to kind of jump, so pardon me scrolling around down here. But specifically, who is this talk for? It's for contributors who've poked around the Rust compiler a bit or a lot. People who are interested in kind of a very technical, general overview of how things work in the compiler. By the end of the talk, I don't think you should know everything about the compiler. I might even get through the whole talk. I have 200 bullet points to get through. But at least y'all should know kind of vaguely like how things are structured, where to start to look for things. It's not a teaching guide of the compiler. I'm not teaching you what a compiler is. You should hopefully know like vaguely what a parser and stuff like that are. It's not a general introduction to Rust, and it's not exhaustive. So generally, compiler's responsibility is to generate a binary. It also generates libraries. It links existing libraries in using artifacts. We have lots and lots of crates, and kind of one of the philosophies of Rust is to don't write things yourself. Along the way, it's responsible for checking that things are correct and sound. Um, Generally, people like to understand compilers in kind of a phasing order. We start with lexing. We take a raw kind of string of the source code and split it into chunks. Parsing turns that into something more structured. We do lots of lowering passes to turn things into more and more structured representations. Throwing away information that we don't know. Things don't exactly happen in this order in the compiler because we have something called a query system, which I will go into detail about. But honestly, it's pretty useful to think about the compiler in terms of phases. Even if things don't always happen in that order, they generally do, and especially the diagnostics you see will often be in that order. But I'll go into the details about ordering stuff like that when I get the query system sidebar. Um, Anyways, we all start at this entry point called run compiler. It's responsible for doing things like parsing all the options from the command line. Specifically, it parses these options into a structure called the session. The session is kind of a mega uber option holder thing. So it holds like the target option, the host option, all the other miscellaneous -c and -c options. It also is responsible for queuing up all the diagnostics we have in the compiler. So when we emit diagnostics in the compiler, they don't go straight to the standard out or standard error. They get queued up and processed a little bit, and we need to link it back to the source files. We need to make it all pretty and colorful. We might have to emit it like JSON, stuff like that. So the session also stores things like that. It also stores some kind of common we don't really know where to put it type things that need to be shared between parts of the compiler, like code stats. Code stats holds the information about type sizes that we end up monomorphizing in layouts, and we just put it in the session because it's kind of a convenient place to hold it. So code stats has a lock of a vector of these like type info sizes things. But yeah, so once the session is constructed, we can use it for parsing. And parsing happens at the beginning in this passes : parse entry point. I'm not going to go deeply into parsing, so I'm not going to jump into this function. I'm going to jump into a lot of functions in this talk. But it does take the session because of all the things you pass to rustc, if you've ever invoked rustc manually, you pass one file and it knows how to compute the module tree based off of all the mod statements in that file. So the only thing it takes is a session, so it knows the input file. And it gives you back a crate. That crate hasn't yet parsed all of its submodules because that happens during expansion because like macros can expand into mod statements and mod statements can expand into macros. So this kind of has to happen in lockstep together. But there's some early parsing options. Like sometimes we just want to print out just the AST of what we've parsed in the main module, or the main/lib module. So we can, if there's -z unpretty, then we will just stop compilation after printing just the parsed representation of the main module. But if we're not, then we go on. So I'm gonna jump into one random function in the parser, parse mod, because I think is really kind of demonstrative of how the parser works in general. Generally, the parser is a function that it takes in some context. So if you're in the middle of parsing like a struct, it might take in whether like a struct or an enum, and then it returns something called a p-result. A p-result is just a result of a thing, and then a parser error, like a diagnostic error. This is just because most things either parse or they don't. So generally, people just go through, it's a recursive parser, so it's very simple. You kind of just consume tokens and then make choices based off of the tokens you've consumed. So for the purpose of parsing a module, we just loop and parse items. We do some recovery because Rust, as Pietro's talk was yesterday, Rust tries to have good errors. So in this case, we try to consume a bunch of, or any number of missing semicolons, because people might write struct with a semicolon at the end of the struct, because that's what you have to do in C. We're going to tell people, no, we don't have semicolons in between items in Rust. and then we push those items into a vector and return that vector, well, or it's a thin vec because we try to be optimized in the Rust compiler. And that's how we parse a module. So that's generally the structure of the parser. It's not that interesting. I could go into things like parsing recovery, stuff like that. But of all the things I want to talk to, I probably want to talk the least about parsing because parsing is one of the things that Rust actually does share with a lot of other compilers. So and the only maybe other thing that I'd like to discuss for people who are writing features specifically in Rust is that we have this thing called gated spans, and it's stored inside the session as well. So whenever you are parsing syntax that is not like ready or is not stabilized, you typically want to associate that with a span, which is it's basically a beginning and end offset in the source file. You want to put it behind a feature gate just so we can make sure to reject that syntax later if people actually try to use it. So in this case, this is parsing impls, like an item called like an impl. And if you write const at the beginning of that impl, that's not a feature that you can use yet. Hopefully by the end of the year we have it though. But it's gated behind the constraint impl feature, and it will later on in a pass called the feature validation pass, we will give you a nice error saying, hey, enable this feature gate if you're on nightly, and hey, if you're on stable, too bad. So that's basically all I have for parsing. But once we have the parsed AST, we will jump into expansion. So expansion and resolution is what we do to turn macros into their expanded forms and resolve most of the identifiers in the in a crate. So we start out with this crate for resolver, which is this is just a way that we can get that crate that we parsed at the beginning, and we pass it into something called the resolver. The resolver basically just recursively walks through the crate, and when it hits a macro expansion, it expands the tokens and reparses them. It reparses them, and it has some complications around use statements and macros, making sure they have a fixed point. So you can have cases where macros expand into other macros. We want to make sure that those macros they're not unstable, as in like if we try to expand them again, they don't resolve to other macros that they wouldn't have in the first place. Yeah. In this process, we also do something called AST validation. So we walk through the AST. We validate purely syntactical things in AST validation. So, for example, things like unions must have at least one field. Other things like that extern types. I'm not sure if most of you haven't worked in the compiler, have maybe never seen an extern type. You can declare an extern type. Extern types can't be generic, for example, because we don't have like template instantiation rules in C++. So once we've done the macro level expansion, we jump into late resolution. Late resolution is something I know a little bit more about, and it looks like my proc macros aren't expanding, so pardon the red lines. But late resolution is responsible for actually resolving all the identifiers and modules and trait items that we have in the compiler. So it's structured. So Rust is naturally scope shaped. So we structure the resolver as a stack of what we call ribs. Ribs are kind of just, they're just mappings of identifiers to things. Typically the thing that the rib is supposed to be mapping is something what we call a res. So res is basically everything that can, and more proc macro failures, it's either defs, which are items, so like things like functions and structs and stuff like that. Some primitives that have special rules. So like primitives aren't actually declared anywhere. There's no like struct i32 in the standard library. So they have to be built in specifically into the compiler. We have some special rules about things like self-ties and stuff like that that have special resolution rules. Different kinds of self-ties, because self means something different inside of an impl versus in a trait. And locals, which are like variables, and then other things that are more relevant to like attributes like tool mods and stuff like that. So the resolver is, as I said before, kind of in a visitor structure, recursive visitor structure. So we visit things like functions. We try to resolve the things that are like in that function by visiting all the things inside that function. And then we record all the resolutions in something that we then use later for lowering. Um, so the one thing I wanted to mention is that lifetimes are resolved kind of differently. They use a whole different rib kind. So uh, they exist in kind of a weird special namespace because they're tick, identifiers, not regular identifiers. And they can be elided. So if you've ever written tick underscore, or if you've ever written something like path, which has a generic and you've just never written the generic on it, we have to synthesize a lifetime in that case. So in order to handle the fact that lifetimes are special, they get resolved specially. And later on, I'll talk about how we actually resolve lifetimes twice because we need to. Um, right. So let me scroll. As we are expanding and resolving things, we also want to we want to give every item an identifier that we can then use later for lots and lots and lots of different things. And we give these items unique identifiers called def IDs. So as we are going through the expansion, we walk through something called the def collector. The def collector, again, is also a recursive visitor. I will say that lots and lots of things in the compiler are recursive visitors because recursive visitors are great for tree-shaped data. But the def collector is responsible for basically every time it encounters an item, it will call this function called createDef, and it will associate some things we need to know about that like its name and its def kind, which is basically what kind of item it is. And then it will assign it a def ID. It will give us back a local def ID is actually just a def ID where we know that the crate is the local crate, but a def ID is just a local def ID plus a crate ID. And then we use that def ID ubiquitously throughout the compiler. So resolution is done. I wanted to take a sidebar and talk about the query system and more proc macro errors. The query system is basically what we use for almost all computation of stuff after resolution in the compiler. So we have this Omni object called the tie context, and this tie context is given a bunch of methods that are declared through this interesting callback called Rusty queries. And most of every query takes a key and returns a value, and it's cached and we can save the information across compilation sessions with incremental. Every one of these queries is backed by a provider. The query providers are just declared in a function. So at the beginning of compilation, we pass in all the providers for queries in a mega table called the providers. And then whenever you invoke a query, if the query system determines that we actually need to recompute the query, for example, if it's the first time that we call a query for a key, or if we haven't cached it or something like that, it'll invoke the query provider. It will take the result from the query provider and hash it and do all this kind of stuff, and then it will store it. And if you call the query again, then it will usually just load the query, the cache query information from memory. Queries can be marked with lots and lots of interesting attributes like separate provide extern. So separate provide extern tells the query provider that it only needs to be implemented for local things, and the way that we get the query results for non-local things, like things from upstream crates, is through another query provider that you can provide. That usually just loads things from tables that we store when we're finalizing the library from the last compilation session. There's things like feedable, which has to do with synthesizing def IDs on the fly, and cache on disk if, which has to do with incremental. So some queries can be very expensive to compute, and we want to know whether or not we need to cache that for the next time we run, so we don't have to recompute it in the next incremental compilation session. Right. So typically, we call queries. I got this link wrong. Typically, you call queries and you want to get back a value, but sometimes in the compiler, we want things to be mostly stage-based, as I said before. So we have, and I'm just going to search this one, pardon. We have something called ensure OK, which means we don't really care that the what the value of this query is. We just want to make sure it's run. So in the beginning of the compiler, we run ensure OK on a lot of different queries, just kind of give things a general order. And then if the values are needed for compilation later on, we will actually call the query and compute its value. So ensure OK just means I just want to make this query, make sure that this query has been run, and not necessarily care about what the value is. More attributes like arena cache make sure that it means that the query provider, for example, closure save names of capture variables, doesn't actually need to return a arena allocated value. It just returns the raw value, and the query will do the caching for you. And then there's some cycle handlers. So the query system doesn't handle cycles. If you have a query that calls another query that calls back into the first query, then it will have an error. But sometimes we want to customize the errors that we have, so we can tell it to like actually don't emit an error. We will emit an error for you. So it will instead delay a bug. So delaying a bug means that we will stash an error for later, and we will check that at least one error has been emitted before this. And if not, then the compiler will ice, which is it will crash catastrophically. So that's the query system. The query system powers basically the whole compiler, and it gives us the ability to, honestly, really simplify the structure of how we handle things in the compiler. We don't have to make sure that data is computed by the time we get to some phase in the compiler. We can just call it, and it will kind of be given to us on demand. It also honestly helps us like have better diagnostics, because if you need some exotic information from somewhere else in the compiler, we just put it in a query and you can call it, and you can basically access things kind of out of order for the purpose of diagnostics and stuff like that. So we have the AST. It's been resolved. It's been put into the query system as an input, but now we want to lower it into something that's a little bit easier to type check. So we have the here HIR, higher level intermediate representation is what it stands for. This is the main data structures that we use to type check things in the compiler. So the here is, and I'm getting more proc errors. Let me restart my reload rest analyzer. Yeah. The here is generally also tree shaped, of course. It is compared to the AST, though, it's immutable. It's desugared, so we lower a lot of things like for loops and dot awaits into kind of simpler representations that we can type check more easily. So we don't have so many special cases in the compiler. It's simplified, so we don't, for example, we don't lower parentheses. We lower tuples because tuples are semantically useful, but parentheses aren't, so we don't lower parentheses. And some state that we have determined from things like expansion and lowering is baked in. So for example, those res structures that are resolution results, they're baked directly into, like, for example, the path expression kind that we have. Typically, things in here are structured like this. So it's basically, we have a struct called item, and inside of it is a kind called item kind. And item kind is where all the interesting stuff happens. That's where we define extern crates and statics and consts and functions and structs and stuff like that. And all of that's shared within kind of the parent item kind structure. And inside of item kind, we just share some plain things that all items have, like spans and owner IDs. So here has its own set of IDs that we only use for here. The main one that you will see everywhere is here ID. Here ID is basically what we use to determine a lot of important pieces of the here using an ID, so we can store kind of data on the side in tables, like type information, stuff like that. Here IDs are identifiers for important pieces of here. Every here ID is associated with a node, and you're able to bidirectionally map between here IDs and nodes. So nodes always contain a here ID inside of it. And nodes can, but then you can load a here ID into a node and then match on what that is. Here IDs are internally composed of an owner ID, as I pointed above, and an item local ID. An item local ID is basically just a U32. An owner ID is important because these are like item level things. So only items have owner IDs. Generally, there's some caveats there that I don't want to get into. But typically, owner IDs are the the building block upon which we do a lot of analysis. So a lot of tables are a lot of tables take owner IDs in and then store all the information both for it and all of its children until we hit the next owner ID. Right. So as I said before, all these IDs are useful for attaching data to type check results. Some queries are keyed off of here IDs. They're useful for navigating the tree in both directions. The tie context, that Uber structure that I told you before, also has functions for kind of getting the parent node of something if you have its here ID, and this is used for diagnostics for kind of walking up the tree. So if you forgot to declare a variable, then we can walk up the tree to the next block and tell you where to put the variable. Yeah. So how do we get to this here, though? I did a lot of explanation, but I haven't really gotten into the detail of, because right now all we have is an AST. So this happens in here lowering, and so all we do is first we take the resolver results and the crate that we process during resolving. We pass it into something called the item lowerer. This is, again, also a recursively defined thing. So it takes the AST version of something and turns it into the here version of something. And it allocates all of the things in here on an arena. And yeah. AST to here lowering is pretty straightforward. It's mostly just validation and kind of shuttling data between one data representation to another. I can kind of walk into it, but it's, again, pretty tree structured. We walk into lowering functions. We match on all the things, and we match on, like, here's lower mod, for example. It takes a mod item in, and it lowers a module by lowering all of its mod children recursively. There's one quirk that I maybe wanted to point out too, is that as I said before, we do processing to make type checking easier between AST to here. So for example, coroutines, which power async blocks, do a bunch of desugaring with its like arguments. So because coroutines are like functions that return async blocks, and async blocks are actually just closures in disguise. We need to take all the arguments and pass them into the closure and make sure they're all captured and stuff like that. So this is kind of the most complicated thing you'll see inside of AST lowering. And I'm not asking for y'all to actually read this, but it's basically just like a lot of processing. A lot of the comments in the lowering context describe theoretical pieces of code and explain how they might be lowered in the here, and then go into actually doing that. Right. So at this point, we have lowered the here, and now we need to do, as I said before, that lifetime analysis part 2, and this happens in something called resolve bound vars. Let's reload Rust Analyzer again because I'm getting more proc micro errors. So resolve bound vars, which I'll call RBV because it's a handful or a mouthful, happens where we walk through the here once again, and we try to resolve all those tick underscores and anonymous lifetimes that we lowered during resolution and expansion. We also at this point re-resolve type and const parameters. This is because we have some features in flight, like non-lifetime binders, that need to know whether some things are kind of higher ranked or not. And resolve bound lifetimes is the first, or resolve bound vars is the first time that we actually have the sufficient information to know whether things are higher ranked or not. So RBV is responsible for doing that. It works on the here and gives us the sufficient information to actually lower into the next representation, which we will call middle. So middle is a pretty kind of vaguely named crate in the compiler. It's the leftovers of everything that wasn't either pulled out into a higher compiler in the crate graph, or a higher crate in the crate graph, or a lower crate in the crate graph. It's just whatever's left in the middle. Typically, though, in my understanding is my intuition is that middle contains all the type system stuff. It obviously contains a lot more, but generally the most important stuff you'll be importing from middle is specifically from a module called middle tie. Middle tie is the Uber module that contains all the stuff all the stuff for the type system. So like, why do we need another representation? Like we already had two at this point. Like, do we really need another? Specifically, middle tie is very useful for us on the types team because it's the representation that has no fluff, no nothing. It has no spans. It's all the syntax has been stripped away. Even a lot of the notions that might be different for users have been kind of abstracted away. Like we treat structs, enums, and unions all as the same thing. We call ADTs, abstract data types, or something like that. For example, like if we lower two U32 types in vastly different parts of the program, they turn into the same tie in the middle representation. It's the cross-crate interface that we use for API level information about crates. For example, here we basically just throw away when the compilation session is done. But if we want to access things from upstream crates, we'll typically access it in its tie representation, at least at the signature level. We also have mirror and stuff like that. Almost everything in Rusty Middle is encodable for this cross-crate reason. Encodable, decodable, so we can store it in libraries. And the lowering process from here to tie is called here tie lowering. So, but I just typically call it here to middle. So it's not ambiguous because if I say here tie lowering, is it going to here or is it coming from here? This is the logic for lowering from here to middle is contained inside this trait called here tie lower. You might ask, like, why is this inside of a trait when the rest of them were just kind of inside of structs? It's because we actually have two of them. We have different contexts that we lower things into the middle layer, and it has to do basically of whether or not we're inside of a body. So inside of the braces of a function or after the equals of a const or a struct, we call this in the type system, we call this a body. Inside of bodies, we can do things like type inference that you can't do at the signature level, or for example, in like a struct field, or like in an extern block or something like that. So to distinguish the capabilities and the responsibilities of these two types of lowering, but also to kind of share all the things that are in the middle, like there's nothing different between lowering a U32 inside or outside of a body. We've abstracted into a here tie lower. There are two implementations of the here tie lower, one inside of something we call the function context, and one inside of something we call the item context. The item context is responsible for item level lowering things. There's a very useful doc comment written by F. Mies, I think, that describes the distinction between the item context and the function context. But the item context is typically what we use to lower things, as I said before, like struct fields and things in the function signatures and stuff like that. It itself also is a recursive lower. Basically just takes something in its here representation, it returns something back in its tie representation. I didn't have a lot of links to this, but there's functions like lower tie and lower const and lower lifetime, which we also call region. So if I say region at all in this talk, what I mean is lifetime, because region is the technical word that we use in the compiler. But if we are not at the signature level, if we're actually within a function, because obviously functions make things go in the world, we need to do something called inference. So you are allowed to write the underscore placeholder when you mean figure it out for me. I don't know what this is. Compiler, figure it out, and typically it will, and if it won't, then it'll tell you. But in order to do this process of inference, we need something to store all the inference state, because inference can go backwards, it can go forwards. It can happen basically only once we know sufficient information in the type system and stuff like that. So the structure that we use to store things for inference is very helpfully called the infer context. The infer context is basically just a bunch of tables. So inference, specifically, inference is the process of, as I said before, checking things. Inference context is basically just a bunch of tables for type variables and other inference variables. We have other inference variables like const variables and lifetime variables. But the one that you might interact with the most is type variables. The inference context also stores all the lifetime requirements that we need to check at the end of running checking a body, because if you've ever talked to anyone in the type system, we may have told you that lifetime doesn't affect type inference, or lifetimes free lifetimes don't affect type inference. So what we do is we basically just take all the lifetime information that we've learned about equating types together and store them in the table at the end. It also stores all the hidden types of opaque infiltrate types that were inferred. Inference contexts are constructed using this build function. So tcx.inferContext gives you a builder pattern for inference, and you call .build, and you pass something called a typing mode, which I don't think I'll have enough time to get into, but it basically just says what kinds of things are you allowed to do at this point. Are you allowed to infer infiltrates? Are you allowed to it has some special behavior on specialization, but this will give you an inference context. And once you have an inference context, you technically are allowed to do things like equate type variables and stuff like that. Like if I have a vec of underscore and I call .push one I32 onto it, we should be able to infer that the inference lifetime of that vector is now an I32 by constraining it by the push function. Right. Inference contexts are useful. We have a whole structure dedicated to it because it's because both it needs to store things, but also it's kind of a nice data structure to work with. It allows us to do things like probes, which is a lot of times in the compiler or in type checking, we need to explore possibilities. So entering into a probe allows us to kind of like do things that might have side effects and then roll back at the end because we only care about, for example, whether or not something works or not. So for example, like in method selection, we want to check all the methods that work. And then if there's only one, then we want to give you an ambiguity error, or we have some precedence rules. We want to check out which impl actually might satisfy a trait because there might be two that apply, but upon further inspection, only one actually applies. We use probing all over the place in diagnostics. However, one thing that inference contexts don't store is they don't store the trait solver state. So like what is trait solver state? So like where clauses, we call those predicates in the compiler. And when you call, for example, a function, you need to satisfy the where clauses of the function for the function to be like sound and valid to call. The process of satisfying those where clauses is what we call like satisfying the obligations. So we store predicates and the obligation to prove that predicate in a structure called an obligation. More Park microerrors. So an obligation contains some T. It's generic over T because we actually use this obligation for more things. A parameter, which is basically the environment in which you're proving things. So like if you're in a function and you have a where clause that says like, for example, a mutable pointer of I32, like ampersand mute I32 is copy, then you can prove the fact that ampersand mute I32 is copy even if it's not true globally. So having the parameter allows us to prove things that we might only be able to know inside of the where clause. And it also, more importantly, allows us to assume things about generic type variables that we don't know anything else about. For example, if we need to prove that some T is implements iterator, then we need to have a parameter, a where clause environment that lets us assume that T implements iterator. It also stores things like recursion depth, so we know when to overflow things in the compiler. But these obligations need to be put into something so they can be processed. And we don't want to make it so that if we prove an obligation and we don't know for certain if it's true, that we're going to fail. So we basically need to hold these obligations in a queue of sorts to process them over and over and over until they finally succeed. For example, if I have a vec of underscore and I want to prove that it's display, vec of underscore, well, debug. If I want to prove that it's debug, vec of underscore is not debug, only if that inference variable underscore is debug. So we might not know yet whether or not it implements debug, but we need to wait until sufficient type inference has proceeded until we can prove that it's debug. So we store these obligations that are in flight in something that we call a obligation context. Let's see. Yeah, the obligation context, which is basically just a inference context, as I said before, plus something that we call a DIN trait engine. I'm not going to go into the details about DIN trait engine because DIN trait engine is only DIN because we have 2 trait solver implementations today. Hopefully, we will be able to fold that down into basically one implementation of the trait solver, and it will just be what we call a fulfillment context. But that ref box of DIN trait engine is basically just a vector of in-flight in-flight obligations that we are in the process of proving. So the obligation context gives us a great API to do a bunch of things like register obligations. So it takes an obligation in, and you can do it for multiple obligations. There's some kind of convenience functions for registering things. Normalization, which is taking a type and kind of simplifying the types, associated types inside of it. So for example, if I have an array type and I say array as into iterator : item, then that normalizes to the item of the array. Yeah, so obligations are the main object that we use to prove things. One thing I forgot to go about obligations is that they also contain diagnostic information. We have this giganto struct called obligation cause code that contains all the different reasons why we might want to prove something to help us have enough context to prove things and also give good error messages. So yeah, as I said before, they act as pending queues of obligations that have yet to be processed. If we process obligations, let me see if I find the select. So select where possible basically tries to compute all the obligations that are in process, and if we for certain know that one obligation fails, we will return it in this vector of E. Obligations are also abstract over the kind of error message we want to return, because we might not actually want to compute all the deep error messages for why something failed, because even computing error messages is expensive. So yeah, and then any leftover obligations at the end of processing, we will also turn into ambiguity errors. So basically, if I declare a variable and I never assign anything to it and I never give it a type, then I need to say this variable has no type information. Therefore, we can't prove that that variable is sized, because you prove every variable is sized. That will happen at the end at select all or error, which is basically just select where possible, and then everything else that's left over turns into an ambiguity error. Right, so the obligation context is one of the things that you can put obligations into and process them, kind of like the distinction between inside of and outside of a body, between item context and function context. Obligation contexts are usually used for proving things outside of a body. Inside of a body, we have something else called the function context, which is kind of the major structure that we use to do type checking inside of a body for functions. So though almost everywhere else, if you want to just create a context to check a predicate, if you want to do it for diagnostics, if you're trying to add extra validation for example, adding a new feature to structs or something like that, you'll probably almost always want to create an obligation context. Right. Obligation contexts and function contexts don't support probing. So if you need to prove something inside of a probe, like if I said if you want to test something out, proving predicates might have inference side effects. So if you want to not let those inference side effects bleed into your program, for example, if you're just trying to validate something for diagnostics, you need to create an obligation context inside of the probe. And if you don't, then I think the compiler will ice. So that is all the context that you need, so we can jump into type checking. So again, I hope that everyone here has written a function in Rust, because functions is where all the magic happens. It contains expressions, and all the expressions have types that fly everywhere. And unlike programming languages like C and Java, you don't have to write all the types everywhere. The fact that you don't have to write the types is, I think, one of the greatest things that Rust gives you, but also that you have the type information like Python. So how does all that work? It happens inside of something, as I said before, called the function context. In this, I'm just going to disable Rust Analyzer. Can I kill Rust Analyzer? So, like almost every other thing I said here, function checking is also recursive. We basically want to take an expression, check the expression, and return what type that expression evaluates to. So this is the entry point into checking functions. So it takes a function context that we constructed. Constructing that function context is not that interesting. We basically just take the root of type checking. So every function is its function root, but inside of a function you can have other things that are type checked with it, like closures and const blocks and stuff like that. Inference variables can flow between closures and const blocks and stuff like that, so we have to check them all together. So a function context just contains an inference context. and it's also recursive. So checkfn, it does some things around handling opaque types, infiltrates. It initializes the locals of of parameters. But the most interesting part of checkfn is where is it? Check return of body tail, which is the entry point into just basically checking, does the body of the function evaluate to its return expression? And the way we can do that is by checking the return expression, and we give it the hint of the return type, and we enter into check expr with hint. Check expr with hint is probably not the function that you'll call if you're implementing new type checking. There's lots of different flavors of this fn check expr star, but they all basically have the same shape. They take an expression or a pattern or something like that in, and they return a tie out. So checkx for hint calls into checkx for expectation. Expectations are basically just saying, what do I know about the type that we're checking from the outside? Where are we passing in to kind of influence things like unsizing and coercions and stuff like that. We also pass in, for example, the args of a call expression, but we eventually bottom out in a function called check expr kind. I think I don't no, I do not have it in here. Check expr kind, and that's the match on all the different expr kinds and check it based off of the behavior that we expect the expression to have. So, for example, literals will evaluate to the literal type. They'll actually usually evaluate into an integer or float inference variable. Binary expressions need to do operator lookup. Assignments need to make sure that the left-hand side is coercible, the right-hand side is coercible, and the left-hand side, et cetera, et cetera. We recursively walk through the here body. We check things as we're going along. For example, as we're going along, we record information. Like, for example, check expr field. When we check that some base type has a field, we're allowed to do auto deref. So we need to store how many times we've auto derefed the base. So what we will do is we'll enter into a loop, we'll instantiate an auto deref, which basically is just an iterator that takes the base type in and repeatedly tries to apply the deref trait to it. And we check if each one of these base ties is an ADT, is it a structure or union, or an enum. And we check that it has the given field that we were looking for. If we find it, we write what the index of that field is, because very commonly in the compiler we don't want to work with names, we want to work with indices, because indices are easier to deal with, and names can have things like hygiene that we don't want to have to deal with. We write the adjustment steps, which is basically the number of auto derefs we need to do. We check things like visibility. We want to make sure that all the where clauses that we get from the auto deref apply. We want to check the stability of the field, and then we want to construct the field type by taking the type of the ADT, taking all its generic parameters and plugging those into the field tie. Right, and then we want to bubble up. So we return the field type, because we want to bubble up this type information for whatever expression this is contained within. As I said, yeah, auto deref is very commonly used in the compiler or in type checking for things like everything that has to do with a dot. We also very commonly do things like coercion. So when we're checking an array, for example, all the array elements don't need to be equal to each other. They just need to be coercible into something similar, or something related by coercion. So coercion is not the same as type equality, because you can do things like unsizing, and these all actually turn into real statements and real machine code in the compiler, or sorry, in the final binary, versus type equality doesn't actually turn into any real instructions. It's just kind of a type theoretical notion of equality. So, for example, here we check that if the args isn't empty, if it's not just an empty array, we construct this thing called coerce many, and for each expression, we check the expression using the hint of the type information we have in the coerce many, and we coerce that type into kind of basically take the type information out, check the expression, put it back in. And then once we're done, we complete the coercion, and we return the element type back up. Right. I'm going to jump over. I was going to go into closure analysis, but we definitely do not have enough time for that. But at the end of type checking, we do this thing called write back. Specifically, write back helps us prepare all the type information that we have. for use in later phases of the compiler. Like specifically, we don't allow us to have any inference variables at the end of type checking. All variables should have been constrained. All inference variables should have been turned into something else. So this is the function in which we actually do this processing if we're solving all the type variables in a body. We create this thing called a writeback context and visit all the data that we store in this writeback context. We store all the types of all the expressions in the tree. We store all the information about all the method resolutions and all the fields and all the pattern types and stuff like that. So yeah, we visit the body, check all the closure sizes, we visit closures, we check opaque types, all the casts, user provided ties, things like that. And then we finally return these type checker results up after Arena allocating them so they're copy. One interesting thing I might want to point out is that we also do a lot of hacks in the writeback to kind of handle lowering to mir, which is the next stage of lowering. For example, 1+2, the built-in 1+2 operator gets treated specially in mir. We don't want to have to do a method call for things that we know are built-in mir operators. So here we detect that if we have a expression that is a unary or binary operator and the node types are scalar, which is basically they're integers, then we remove the fact that we basically remove that they're method calls at all, and they fall back to being built-in mir operators. All right, so that's type checking. Between type checking in the here level and lowering to the mir level to do borrow checking, we have one middle phase in the middle that we call typed here or thier. I don't know if everyone calls it thier, but I do. You could also call it tier or whatever. But typed here is basically just an intermediate representation between here and mir, which we use to kind of elaborate even more of the information that we've inferred during type checking. We lower things into a table. Into a table-based representation rather than being a kind of a substituted, or not a substitute, an arena allocated kind of tree shape structure. Let me see if I can find expr kind, and jump into it. Also, pardon again for the red, but we lower all the expressions into a very simple representation, like a box just contains an expr ID. Expr IDs are just a mapping from ID to expr kinds, or they're actually thier exprs, which contains expr kinds. We store extra information that we didn't have before, like scoping information, which is very important for mir lowering. We simplify things like method calls into just basically every single call is just the same kind of call. And we want to store some extra information like, does it come from a here call operator? Does it come from something else? Because we can lower different kinds of calls based off of things like derefs and stuff like that. Right, so again, it's the same kind of structure. We walk through, we visit here, we emit there. The lowering is pretty straightforward. Basically, we just pass in for example, a here expr into something that's typically called mirror something, and that mirror something will return the thier version of that something. We do some more analysis, or we do some slightly more analysis. Actually, no, we don't do that here. And we allocate it into something that we call a steal, which I kind of won't get into. Two things that we do on thier conveniently is we check patterns using the thier, because having all that type information kind of baked into the thier is very, very useful for checking pattern exhaustivity. Otherwise, we'd have to be looking up types from patterns, and we'd have problems around things like implicit pattern derefs and inference and stuff like that. We also check unsafety on thier. I can't exactly remember what the motivation for checking unsafety on thier versus mir is, but it's probably a good reason. And we do those both before lowering directly to mir. So mir is the last IR that I will talk about. It is the simplest representation that we get before we do cogen. It's very flat. Typically, statements in mir are not tree shaped. They can't have like complex expressions inside of them. They're typically just like local equals, like a local variable equals, and then some very simple expression. And if you want to, like, we lower like maybe a very complex expression to like 10 or 15 different mirror statements. Um, so uh, mirror lowering, I didn't have a bullet point for that. Mirror lowering is, give me a second. Uh, Mirror is conducive to control flow graph type analysis. Expressions and statements in here are flattened to very simple operations in mirror. It's easy to do, as I said before, flow-based analysis and transformations, things like drop elaboration and coroutine lowering, and borrow check on mirror. And the first thing, and I think the only thing I'll be able to get to in the mirror level is that we also do borrow checking on mirror. And this is because borrow checking has this kind of graph-based, flow-based analysis that is a lot more conducive to do on mirror than on here, because here is naturally like scoped and naturally lexical. So that's why we have non-lexical lifetime and a non-lexical representation of the program. So borrow check is pretty straightforward. Let's restart the server one more time to get rid of the red. It takes the mirror that we lowered, and because the mirror is a completely different representation than the here, we have basically no connection between the mirror and the here. So all the lifetime information that we computed during here, we basically just throw it away. We need to recompute all the lifetime information that comes from where clauses on calling functions. Like if I have some function that you call and it requires that t is static, then we need to compute that requirement somewhere. So we do this by running type check over again. We first take the mirror body. We take all the lifetimes that show up in that mirror body, which are represented using something called the erased region, which means we don't know anything about the region information. For example, CodeGen doesn't care about anything about regions. So we take that body that has a bunch of erased regions in it. We give every single lifetime a unique identifier. Then we do type checking on that. This type checking is interesting because all it's doing is type checking the program to get its like region constraints for. It doesn't expect any type checker errors to happen. No failures are expected to happen if we find some type of like type mismatch in the mirror. That's either because of a lowering problem or something that wasn't being checked correctly in here. So we walk through this body, we retype check it one more time to get all of the region constraints. We visit the mirror one more time to check basically where things get initialized and where things get deinitialized. And in between those points, whenever it is initialized, it's called live, and therefore it needs to have a valid region. Then when we have all this information, we throw it into a graph. We process it using all these graph algorithms that I don't really want to get into, and we check all the constraints are valid. We basically say that we know that, for example, some lifetimes can't that only outlives these other lifetimes. We will emit errors based off of that. So we enforce the liveness constraints by computing all the things we know about this graph and then walking through it and processing all the informations. We try to take these region errors that are typically pretty abstract and turn them into good errors. I think the name was like 3-part error is what the philosophy of NLL is you want to say where it's initialized, where it's being used, and then where it's being used again where it's not valid. What did I mean here? Yeah, so once we do our solving, then we process through all the regions and we emit errors. And I think that's the last analysis that we do before we get into like linting and CodeGen, which I don't think I'll have enough time for. Another thing that we need to do during borrow checking is that's actually where we infer all of our infiltrate opaque types, because we need to know what the value of the infiltrate opaque type is, like considering all the lifetimes inside of it. And as I said before, we throw away all the region information from here type checking. So we actually have to do it once again in borrow check. So I think people like to joke, for example, that we could just like not run borrow check and the program will run perfectly fine. It's like actually it won't, because we still need to compute the hidden types is what we call them of here. We do compute it kind of in the here as well, but for the whole process to be sound, we have to recompute it in here type check, or sorry, in mirror type check and in mirror again. Right. I wanted to have one more sidebar about foreign modules, upstream libraries and stuff like that. So as I said before, you can mark some queries with extern, separate provide extern, and like this one, type alias is lazy. So we have a feature called lazy type aliases, um, and we don't want to have to recompute if that type alias applies to that feature. When we're in a downstream crate, so we save whether or not this type alias is lazy. We record it in this final step when we're encoding libraries, where we just record a bunch of things into tables. And that's, I think, it. So yeah, I know there's a lot. I didn't go into nearly as much detail as I needed to. I'm happy to answer questions, I think, after the session, because I don't think there's going to be enough time to discuss things in a session. I used to have this thing where I used to go through things in much, much more detail than this. I kind of stopped doing that. I might start doing that again. Online on YouTube, I think there's one deep dive about methods that I went into a lot of detail. I think people told me that it was useful. But yeah, thanks for listening to me yap about the compiler for the last 60 minutes or something like that. I think that's it.
Thank you very much,
Thank
Michael.
you.
As Michael said, we don't have time for questions right now, but I am quite sure he'll be very happy to answer any questions you have around the conference.
Yes.
We have a few minutes break, and the next talk starts at 10:45. All right, welcome back to the Rust project track. Next up, we have Antonio Piraino, who's been contributing to the Rust project in various forms since 2018, and he's going to tell us about contributing to the Rust compiler with little to no code. Give it up for Antonio.
Hi, hello everyone. Feels a little bit strange to be again on stage. I think the last time it was many years ago, before the pandemic, and I remember I brought to the stage, this project when you start learning a language and you are proud to build up a project, an amateur-ish project, but it works. So it was a talk like that. Many years many years later, I am again on stage and in a different role. So, but what is my role? What do I do? Do I write? Do I don't know. I'm in the Rust project. I'm in the compiler team, but do I write patches? Not really. Not in the main repository. Do I do reviews? Not really. Do I understand what Michael said before? Not much. But yeah, there is other aspects of contribution in the Rust project that are equally important and necessary, even if not always really visible. So I started as Adam said a few years ago with small meetups, conferences. It was really fun organizing conferences. And then I got into this working group, the prioritization working group, which is a notification group that basically keep an eye on regressions. So when the compiler does something that it did not, we receive a notification, there are issues, and then we see what it's about. So is it bad? Is it not? Should be solved or will be an accepted regression? So this kind of work is ongoing and ensures that when the Rust compiler is released, there are there is no nothing that we want to slip into the stable compiler. Then all the contributors were merged into the compiler team, so I was kind of merged into the compiler team since then. So if there is a sentence that kind of represents me, it's this assigning priority, because this is the core of the prioritization. When we look at these regressions, we have to understand how important are they or not. And I don't know how many comments like this I posted, maybe more than I can remember. And so this is not only the only thing that I do. There are other things that are ancillary work to the Rust compiler. All these acronyms are basically just tools that the compiler team gives to contributors and newcomers to interact with the team itself. So if you have a proposal, if you want to get in contact with the team, if you have an idea, the major change proposals, RFC, are all tools that anyone can use to get in contact with us. So the thing is that there are many proposals, so sometimes they need all to be followed up. Sometimes they are forgotten, sometimes the author is not replying, sometimes we as a Rust project should provide an answer. This is a follow-up that needs to be done in order to keep things going. Another interesting thing that I do is monitoring patches, incoming patches. This is a bit embarrassing for me, but I have a markdown file in which I do bookkeeping of the pull requests that are waiting on reviews. I have a tool inside the triage bot, which you are probably all familiar with, that generates a list of pull requests that are waiting on reviews, sorted by the oldest. And using an advanced tool called grep, I compare this list with this bookkeeping file, and I keep note when and who was mentioned about this pull request. Why cannot this work be completely automated? Why do I do this in part manually? Because there is one thing that I really care about working while working in the Rust project. We have, on one hand, a finite amount of resources. Contributors, they have their time, they can allocate only a finite amount of time, and so I see them as a precious asset of the project. On the other hand, we have open gates, and we have like an infinite stream of incoming patches. And on the other hand, I understand that external contributors have expectations. I submit a patch, I expect something to happen in a reasonable amount of time. So there is this kind of tension between reviewing patches and doing them in a reasonable amount of time. So what I'm trying to do is to keep these pull requests being reviewed, being active, but not stress too much our contributors, because otherwise I can understand that it can become a bit annoying. Then we have the meetings. The compiler team has regular meetings. We have a weekly triage. We have design meetings, which are so it depending on the topic. We review the past week. We review if there are regressions. What's the situation? Are we close to the release? Do we have things to backport? Do we have unattended regressions? Who can do what? So this is more or less the place where where I, on one hand, summarize. I get input from the contributors if I have questions, and I try to summarize everything in a easily digestible way for the people attending the triage meeting, so that we can have a glance of what's the situation. We have the design meetings, of course, because when there are some topics that are more beefy, they have more substance, we need to dedicate some focused time on that. So these meetings have to be discussed, people get to be invited, and so on. This is also part of my work. Of course, there are documentation, there are small patches. I contribute a bit of patches here and there on the triage bot, for example, or sometimes on the tool that we use to bisect code, the cargo bisect, which is, I guess, some of you are also familiar with. And yeah, now we have our documentation thanks to the work of David. We have the work also on the Forge. So now it's centralized with the documentation of the library team and the language team. And this is important because we have one place for everything. So I kind of see my job a bit like this power generator in a basement that does work, maybe not visible work, but still important, because a power generator gives electricity and lights to the other room where the party happens. And so I feel kind of part of this group of people working inside of the Rust project, doing work I would define fundamental work, but not very visible. Like you're probably familiar with the infrastructure team, which really literally keeps the lights on. And then there are also another group of people doing triage of issues and other pull requests. So we are kind of, I would say, a swarm of little bees going around flower to flower and trying to keeping things tidy and cross-pollinate everything. So what do I see as the next step for my work? This prioritization working group has never been exactly what I've been doing since ever. So learning from the language team, they have this operation sub team, which is TC. And I thought that we could also have this kind of formalization of the work. Because looking at how the language team works in this respect and how the work done by TC, I think it's a really good thing to have. So a couple of days ago, this pull request was merged. So there will be a little change of names, and we will have also this operations team, which should be the entry point for the kind of work that I'm doing. We will add some more automation. That's a continuous process. Of course, everything can be improved and automated. So learning from also the documentation team, the Rust doc team, they, for example, look at the backports, at the regressions, at the patches fixing regressions on Zulip instead of doing that synchronously during the meetings. I like this way of doing this kind of this work, so we will have soon also in the compiler team. So as you can see, I kind of look at how other teams work, and I try to see if there is something that we can bring also into the team compiler to improve our processes. The other advantage I see is that if we as a project try to have a more standardized way of working and replicate the same workflows and the same processes across teams, this is an advantage for the project itself, because from an external point of view, I am outside of the project, I look at the project, and I see that more or less teams work the same way. This is an ongoing work, so I think I want to do more of this in the next months, trying to get the teams maybe look like a bit more cohesive. So that's more or less what I wanted to do. That's a very short talk, my 15 minutes of fame. I just wanted to say that, of course, my work is not in a void. It's not happening in a void. Without every one of you here, it wouldn't be possible, because I really don't have context about everything. It's impossible. So I often have to rely on each of you when there is something that I don't understand, that's something that is a bit obscure. So this is really a community work, and I'm really grateful for each one of you helping me doing this, because otherwise it wouldn't be really possible. So if this work sounds interesting, if you would like to know more, just get in touch with me. You know my handle on Zulip. And one last thing I would say is that since we have this anniversary of the 10th year of the release of the Rust project, let's not forget to party and fail.
Thank you, Antonio, and thank you for all the work that you do. That was great. Okay, once again, we're at time, so we don't have time for Q&A right now, but I know Antonio would be very happy to talk to
I
people
will be
just
stuffing
outside.
myself so yeah.
Perfect. Okay, so we have a break right now. There is some catering downstairs, and we will be back at 11:40 with the next block of talks. All right, welcome back to the Rust project track. First up, a special message, as Mara has already said to some of you. If you have seats in the middle that are currently unoccupied, please consider compressing yourselves so that people who come in during the talk are less disruptive to others. Thank you. It's impossible to put on a conference really of any size, but particularly the size of Rust Week without sponsors. So we'd particularly like to acknowledge Espressif and Phlox, who are both bronze sponsors. They have booths downstairs. They would love to talk to you about the things that they are doing, so please consider going and having a chat to them. All right, and then without any further ado, our next speaker is Jacob Finkelman. Jacob has used Rust since 2015 and has been a member of the Cargo team since 2018 and is going to talk to us today about From Simple to PubGrub, the evolution of Cargo's resolver. Please make him welcome.
So this is not going to be quite as intense a talk as some of the others we've had today, despite how dense the code gets at some point. Another topic, these have desynced. That is annoying. Where's my mouse? There we go. I'm not sure how to kill that. So let's come back. I tried to get this right. I tried to be prepared. Nope, that's not helpful. That's even less helpful. Let's try this again. There we go. Yes. He's a good boy, even if the slides are not being a good boy.
What is the good boy's name?
Harley. Okay. And then I go into presenter mode. Does this work? Yay! Okay. Alternative introduction is what does a dependency resolver do? Why is that a hard problem? Where is the technical debt hiding in such as even the simplest solution we can come up with? And why would we possibly consider a rewrite? Why is that the right solution? I'm Jacob Finkelman, but I've already been introduced. First off, thank you to the staff who's putting on this event. Mara is the one I've been interacting with the most, but that's only because I haven't had the opportunity to interact with the others who are working just as hard. Thank you to all of them. Next important thing, this is based on a true story. No primary sources were harmed in the making of this film. Historical events have been retold to make the narrative better, and code should be considered pseudocode to explain the point. Don't correct me if my syntax isn't right or if I'm using new idioms that weren't around when I say the code is coming from. So cast your mind back some 11 years. We are shortly before Rust 1.0, and you are working with Cargo or on Cargo. There isn't really a distinction yet. It's still a private project. Therefore, you are Yehuda Katz or Carl Lurch because you've just been hired by Mozilla to make a new package manager for Rust. This isn't the first package manager. It's the third or fourth, depending on how you count. The others are dead because makefiles really do work for the C and C++ community that most of our community comes from. So it's a bit of a long shot, but we want a package manager for Rust 1.0, so let's give it a try. We have a lot of important decisions to make. One of which is to design a dependency resolver. A dependency resolver is the part of the code that takes your list of direct dependencies and some source of information about what versions are available and what their direct dependencies are, and returns these individual crates need to be built in order for your project to continue. This is, of course, kind of academic, because given that you're the only two people who have access to the Cargo repo, there are no crates that are compatible with Cargo. There is no crates.io. You still need to write that. Someone could do a good talk about writing crates.io before you had any web libraries, because you didn't have any libraries because you didn't have crates.io, but that's someone else's talk. There are many decisions you need to make that are very important and will change the shape of what it's like to use Cargo. And none of those are about this talk. Those were thought about carefully and did not lead to technical debt. The This talk is about the things you tried to keep as simple as possible so that you could move on with your life, and how that comes back to bite us because we succeeded. So the shape of a resolver, and luckily we have a very big screen because I did not lay this out nicely for you guys, is that it's a function. It takes in a vec of dependencies that need to be solved, that your root crate has some dependencies, and a registry, which is some API for figuring out what's available on crates.io, and it returns either a set of exact versions to build, or some kind of error. We'll leave it string for now because we're trying to keep things simple. So what's the simplest thing that could work so that we can write some tests that test all the rest of cargo? If you don't have any dependencies, then you're done. You just return the empty set, and it's all good. Now you can write a whole bunch of tests for all kinds of other hard problems. But eventually, you're going to have to come back to this. What if you have a dependency? Well, if you have a dependency, then you need to ask the registry what versions are available that fulfill that dependency. There's all kinds of hard engineering in that define what it's like to use cargo, which, as I said, is not the point I'm trying to make in this talk. You then go through those versions one at a time, and you see if they are compatible with the previously made decisions. Assuming that there's a little out of order, we haven't made any other decisions, but we will in a moment. Again, lots of hard decisions about whether you're like NPM and let lots of duplication happen, or like Python and only have one version per name, and all of that gets shoved into that function and is not the topic of today. And once you pick, if it works, and you pick a version, then it has some new dependencies that need to be added to the mix of what needs to be solved. So we have now successfully added one dependency off our stack, and we need to do all of them. So let's just use recursion, because it makes things simple. You need to change the name of the function because it's got a different signature, and you need the state that the previous calls had figured out in your API, and then if you have another thing, then you need to resolve it. If it works, you're done. You found a solution that works. Otherwise, you continue through the loop and try the next version. This is the simplest thing that could work, which is, I said, was our goal, but there's a problem, which is that we have two local variables which are getting handed off to the recursive call and going to be saved for the next iteration of the loop to get handed off to the next recursive call. So we need to add two annoying clones here, which I know looks like an implementation detail, but it will come back to bite us later. So, okay, now we have something that compiles, and we have one more thing to deal with, which is what happens if you run out of versions to try, which is you fail. And because it's a recursive stack, maybe the next one will recover for you, or maybe this goes all the way to the user, but the only thing you can really say is we tried them all and they didn't work. So, okay. Congratulations. You have a resolver good enough to release cargo publicly and see whether people are even going to try using it. And this has a bunch of pros to what we've written. It is clear why it works. Its argument for correctness is that it tries everything. You can see in the code that it actually does that. It has some cons. Let's go into those details. First, those clones are going to bite us. We're cloning a lot of big data structures, and we would like to just slap RC on it, but it turns out that our access patterns mean that RC doesn't actually help that much, so we need a bespoke data structure for each one that clones the minimum amount, and you end up like using a linked list because it actually works pretty well here, and when you're saying you're using a linked list because it works well, you've got bigger problems. A lot of design effort goes into, over the decade, futzing with these structures to try and balance costs. But another thing is those access patterns. We are cloning because we might need it in the next iteration of the loop. But a lot of times, especially if you have a lock file, there isn't going to be another iteration of the loop. There's only one thing that could match. So it's really important that you check if your last iteration of the loop, and then the code's a little pseudocodey here, you take the value, leaving yourself with none so that you don't do a clone. Otherwise, you do the normal clone. Okay. And then we get real users who want more than 20 or so dependencies, and we blow the stack because we've built it recursively. So we need to rewrite it. It's a fairly mechanical rewrite, but to have an explicit stack that we push onto and then pop off of, and then update our local variables to match the ones we pulled on, except when we're going the other control flow, because we're no longer using control flow constructs. We're actually managing our stack ourselves. And this is mechanical, but it does lead to an unreadable mess where the control flow is buried in the middle of a loop, and where, I'm sure you're thankful, we run out of room on my slides for code. So that is the last code we are going to show today, because we need to be thinking at a higher abstraction level. The code has gotten too complex. Ta-da! We have a resolver that can handle dozens of dependencies. It's good enough for people to actually, not just the test suite to try it, but for people to try it and actually figure out that cargo is actually pretty nice and we should actually use it. And it works well when things go well. Less so when things go wrong. Let's look at an example of that. I'm going to go through this one a little slowly. We have an example. We have a libfoo. Libfoo has some dependencies. It depends on useful at 1.0. It depends on irrelevant at any version. It depends on problematic at any version. The names are suggestive. So the first thing we pop off that list is useful. We look it up. The only version that matches is 1.0. And we are still left having to deal with irrelevant and problematic. So we pull irrelevant off. We pick the latest version, which happens to be 1.9. And we have problematic on the list. So we pull problematic off. Turns out problematic adds something to our list because it depends on bad. Again, a suggestive name. So bad, it turns out, does not exist in the registry. So that's already a problem. So we go up the stack again. And now we try a new version of problematic, because maybe bad was added in the most recent version. But in fact, the previous version also depends on bad. So that fails. And then we try another version of bad, which doesn't work. And now we go back up the stack. Now, you and I are looking at this and saying, why did we stop here? Clearly, we should take all of this together and say something like, every version of problematic depends on bad, and you depend on problematic, and therefore you can't be built. Irrelevant is irrelevant. But you've seen the pseudocode we were just running. None of that thinking is in that pseudocode. So we're just going to have to try the next version of irrelevant and see if that helps things. Which it obviously doesn't, because we haven't changed anything about problematic and the fact that it depends on bad. So we load in bad again and check, does it exist? No, it doesn't exist. I'm going to skip over the next 20-something steps where we discover that every version of irrelevant doesn't help, and every version of problematic has the same problem. So takeaways from this. Even in simple cases, we do an exponential amount of work if things go wrong. If we kept track of what went wrong, we could save a lot of time, and we could make better error messages that actually explain what's going on. We could also look to try and do some kind of synthesis where we notice and combine them into bigger statements that are more useful. But until we do that, we do not have enough information to give a useful error message. Let's do another example. I will make it shorter. We've now updated our dependencies. We now depend only on less problematic. Useful is 1.0. Skip over. Less problematic at 2.0 also depends on useful. It has a caret dependency, so it could be on the latest version, but the 0.3 version doesn't work. Why? Because we already picked the 1.0 version. So we're going to have to try them. And at this point, we've noticed the pattern. And so we as humans notice the pattern, and we should say, okay, it's beyond us. We'll just throw out, this isn't going to work. It's the same as the first case, except it's not, because the next thing we try works. The takeaways from this is we need to not only keep track of what went wrong, but exactly why. Because if you miss why, you get the wrong information. You skip over things you shouldn't, which is a correctness problem. And also, if you have the right information about why, that is helpful to the user in the form of error messages. So now we get to about 7 years ago in the Rust 20 era. I am a new to open source programmer trying to figure out how to contribute to the Rust project. I am looking to understand NP complete problems, and this is the only one that's been implemented in Rust, as far as I can tell. Nowadays, there's a talk on it later I plan to go to, but at the time, Rust is growing rapidly, and cargo is a key piece of that. It regularly happens that people add a dependency, and everything just sits there, usually for a couple of seconds. Somebody donated a month of their laptop time to discover it wasn't doing anything. It never solved. So this is a problem I can dig into. And we know the shape from the previous discussions. So the first thing we're going to do is we're going to add what I called a conflict cause, which says every time we say, oops, we can't use that version, we store why we couldn't use that version. And then when we're jumping up the stack, we can say, is this problem still there? Well, then jump up the stack further. And so we can, and if we get to the top of the stack, we have just hit a problem, and we can explain to the users, there may be many other things that went wrong, but the last thing we tried didn't work for this reason, which when you have dozens of dependencies, is usually good enough to figure out, oh, if you were in this branch, then it must have been that other thing that was the problem. There are only so many things. A human can figure this out. The next kind of thing you can do is you can store them. Instead of discovering that bad doesn't work and then trying again and discovering that bad doesn't work, you can record, hey, bad isn't going to work. And then the next time you load in bad, you say, do I know any reasons why it's just not going to work at all? Okay, we can just pop up the stack again until we're no longer depending on bad. This is a fun data structure for supporting it, but that's a different. We can add a bunch of those generalizations, those optimizations. They're called minimizations because you usually end up with a simpler explanation afterwards than you started with. If A will cause B to be required, for example, you have a dependency edge, and we have a conflict for B, then we should be able to write a stored conflict of the form, we have a conflict for A. Of course, that's easier said than done. We need to exactly match in this generalization code the semantics of our just try all the versions, and if they ever come out of sync, then you get really obscure bugs. So, where are we at? Pros. Cargo no longer hangs on any of the examples that people were actually submitting. This is really nice. We sometimes even give those OK error messages, which is a huge improvement. There are cons. Nothing about this is simple. I stopped sharing code for a reason. Lots of the pieces need to match. You can't just make a change somewhere and assume that the rest of it's going to compensate. They all need to have their different representations, and they need to match. And why is this all correct? Who knows? It seems to work. I understood each piece of it as I added it, but the results, I was a new programmer. So we are now in the, it's a mess and it's hard to maintain. If you're not sure what changes are safe to make, the next logical thing to do is, well, that's what tests are for. So let's go from a couple of example tests, dozens of example tests. It's really, but there are an exponential number of corner cases, so dozens doesn't seem so good. So extensive testing that randomly generates thousands of cases every PR and spits out a reproducible example if it doesn't work, and we verify it by having a separate implementation using a standard SAT solver, they're now available in Rust, that may not have the performance characteristics we care about for production, but we can use it in testing to see if we got a correct answer. And it is really nice. It prevents me shipping lots of bugs, mostly by preventing us shipping much of anything. So looks like things are hard. There are a couple of things that ship. I'm exaggerating a little bit. A little anachronistically, this guy whose name I'm not going to be able to pronounce made a very good point in his PhD thesis that DPLL is an algorithm for SAT that roughly has the shape of what we're working on, that is correct because it kept track of all the things it tried, and when it runs out of things to try, it's correct. You might have side tables where you skip over things you know aren't going to work, but the fundamental argument is I tried them all. And there's an extension of that in the SAT world called conflict-driven clause learning, where you generalize some things and you end up with a proof that there is no solution. And he points out that is also profoundly simple because the proof is the only thing that counts. The thing you try next, you can just throw it out and start over. Anything you haven't proven, you try the first one you try. It either works or you prove that that doesn't work and combine it. So where do we store truth? We store truth in the stacks of things we've tried, the conflict clauses, and the exact semantics of the dependency code. We could combine conflict clauses and the stack if we always had one of those proofs for why something didn't work. That always is going to be a lot of work, but if we did it, we could even get rid of the semantics of dependencies if instead of having code that did it, we somehow represented them as a conflict ahead of time. So the code would say, we read from the registry some data, we turn them into conflicts, we add them to the conflict clause and the conflict cache, and then we continue evaluation until there isn't a problem. Of course, the representation I described for a conflict clause isn't sufficient to do an if-then statement. You need a slightly better one. This is where pubgrub comes in. We could have something simple if we just had better and we could use it consistently. Natalie was assigned to build the package manager for Dart and did a lot of research and came up with some insights. One is that requirements are better thought of as a mathematical set of things that could match rather than an iterator of things that did happen to match. Of course, it's easier to say that if you're building things from scratch than if you already have a complex iterator that decides what matches and you have to match it. And she also generalized what we had been calling conflict, but other people had other names for, into incompatibilities, which can store all of the different kinds of things that we need it to. She has a great blog post announcing it, which is well worth reading. So the other important thing about incompatibilities is because they're mathematically defined, you can decide if a optimization on them is correct outside of the context. You can look at two incompatibilities and mathematically prove that that a third incompatibility represents the other two, and then you can decide whether to use that or not. But none of this depends on the semantics of what dependency resolution you're solving, so you can test it independently, which makes a huge difference. Of course, in order to get all of these benefits, you not only need to have an incompatibility that represents your semantics, you also need consistently to use it and never have something that reaches through a back channel to see based on the order of operations. It is much easier to be consistent and disciplined if you start from a clean slate. So the pubgrub RS library was born as a way to experiment and build an implementation. I have a talk from 3 years ago now about the details of how that library worked then, much of which is still the same, if you want to see that. The pubgrub RS library is in production use. The Gleam programming language uses it for all kinds of things. UV, the very popular package manager for Python, uses it in production. So a lot of good feedback from them about what needed to be improved to make it work. And there are a handful of other semi-production and production projects that use it. It is actively being tested versus Cargo. We have a separate project that downloads all of the crates on crates.io and checks that the resolution you get if you use the Cargo resolver and some scaffolding around PubGrub are close enough to being the same that we're confident in it. We're still tightening the screws on how close that is and tracking down problems, mostly performance problems in Cargo and correctness problems in our lowering to PubGrub, but we're still working on it. And hopefully I can continue on that project goal soon and we can get a Z flag in Cargo. And so that is the end of my slides. That is the state of affairs. I'm open to questions. Yeah, the key takeaway here is that's what resolution is and why it's hard, or if you're in charge of project goals, that's why I have a project goal that considers a rewrite when the rewrite should be your last possible option. Yes, now I'm ready for questions.
Thank you, Jacob. Do we have any questions? We have a few minutes. Okay.
Where do feature flags fit into this?
So, in the current resolver, they are one of the gnarliest of those details of exactly what things match your query that then need to have the same semantics in our representation of conflict. One of the causes of conflict is this version has this feature flag. And then you also need to track why does it have that feature flag. And if you wanted to support weak features, which is a fairly recent addition, you would also need to know both who added the weak feature and who added the thing that activated the weak feature. And that was complicated enough to get right, despite two of us trying pretty hard, that we just cut it out. It does not affect your lock file, and that is annoying, and I get complaints about it regularly, and it's because getting the semantics to match is just too hard. In the lowering to PubGrub, we solve it by representing them to PubGrub as separate packages. So foo is a package, and foo's feature bar is a package that has to match the version with foo and has some other dependencies, which we'll have to figure out how well that works. There's a reason it's not merged in yet. It gets the correct answer, and it is better at some performance problems that we care about and worse at other performance problems that we largely don't, but details to be figured out.
Okay. Since I'm already down here.
Thanks. So you said you were verifying against a SAT solver, but it wasn't performant enough.
Yes.
So I'm just curious, how not performant enough was it? But then I have a second question, which is, did you look into mixed integer programming at all for doing the solutions?
So the biggest problem with performance is less the actual performance of it and more the characteristics of that, what kinds of things are slow, what kinds of things are fast. Also, we want to pick the best for some local definition of best, which means that we're not looking for a SAT solver, we're looking for a max SAT solver. And you're right that actually mixed integer programming is often a better choice when you're looking for max SAT, but life gets complicated. Also, when you lower to SAT, we need to pick one of these ends up being a lot of XOR requirements, which is the thing where SAT solvers fall over. So by building our own, where that is one of the basic operations, we remove a lot of the slowest cases at the loss of not having a huge community of people helping us optimize it.
Okay, I think there was somebody up here somewhere.
The other thing that happens with a SAT solver that hopefully won't happen as much with PubGrub is that SAT solvers will say, a nuisance variable you added over here to express your exclusive OR is incompatible with a nuisance variable over here about a different XOR, and explain that to the user. Like, how? What do these variables represent when it's done simplifying it? I have no idea. How am I supposed to explain that to the user? Whereas PubGrub, at least the first two layers of abstraction are things people know about. When you say this set of versions, that is a version requirement that is in a syntax you had the user write. And when you say an incompatibility of this shape, most of those, at least the two-length shapes, are things that a user knows about. A negative and a positive is a dependency edge. I don't care where it came from. You can explain it to the user as A depended on C. We derived that from something, but that we can explain. Yes, it's isomorphic to all the others. There are cases where our explanations fall apart, but I have hope that it will be interpretable for the simple cases people actually hand us.
Yeah, sorry if this is repetitive, but maybe this is going to be a simpler version of this question. So as I'm understanding it from this, it's essentially kind of PubGrub is a custom max sat solver for this problem.
Right.
What is the motivation for building it from scratch in Rust as opposed to interfacing with existing sat solvers? Because I do know in other contexts, I'm not super educated, but I do know in other contexts, right, you might just interface with an existing sat solver that someone's already defined, and that runs relatively fast.
Yes.
Is it a performance problem? Is it about explainability? Is it fun?
It's a little bit of all three.
Okay.
There are performance characteristics that are different that we don't have control over. There are trying to get the error messages to make any sense. There are advantages to writing it ourselves. The reason to rewrite it in Rust as opposed to using a PubGrub implementation in another language is that while PubGrub is algorithmically fast, the details really matter, and we can write it faster in Rust than any of the other implementations. Small VEC optimizations turn out to be really important, and they're annoying to do in a garbage-collected language. You've got one behind you.
Perfect.
Hey, Jacob. Thank you for the puppy tax to start the presentation off. So right now, PubGrub is being, you said, verified against the existing solver. There's a lot of correctness checking. Meanwhile, UV and Gleam just said, good enough, let's send it? Or is that because you're trying to maintain back compatibility? Is there a different standard of correctness? Like, why are they just full steam ahead and, you know, like you're still doing work on this?
We have extensive tests of PubGrub. A lot of the testing infrastructure that worked for Cargo could be copied over to the PubGrub implementation and simplified because it's a simpler model. So it has very extensive tests. For the problem it solves, I'm quite confident it gets the correct answer. UV did extensive testing for the extensions they needed to make. Does it get the correct answer that got them comfortable? The part where I'm still testing and moving slower than other people would like me to is when I modeled Cargo's dependencies into PubGrub's incompatibilities, did I lower it correctly? Or do I have slightly different semantics between them, which means that PubGrub thinks there is an answer when Cargo thinks there isn't, or vice versa?
Okay, we probably have time for one more. I see one down the front there.
Riffing off of what you just said, would it be feasible to, say on like nightly builds, run both resolvers and then just report when they diverged, if they ever diverged?
Yes.
Is that the plan?
That is, currently we need a Z flag that even gets it in so that we can run it internally. I would assume, but it is up to the rest of the Cargo team, that one of the next stages is it runs in shadow mode, and if you turn on the Z flag, it tells you if there's a problem, if there's a mismatch, or it tells you to open a bug report. And then we'll switch to, because PubGrub probably has more correct, if not more readable error messages, if there's a correct solution and they agree, wonderful. And if they both agree that there isn't a correct solution, we show you PubGrub's one. And if they disagree, we tell you to make a bug report. And then we'll have to see if we can actually remove the old code, or if we end up needing both of them to support old versions of the resolver. But this is vaporware several stages down. But yes, that is the goal.
All right, I'm sure Jacob will be more than happy to talk to people about this for the rest of the conference and at your hands. But for now, let's thank him once again for his time. All right, in about 10 minutes, we will have Ed. Stay tuned. All right, Rust Station friends. We have one more talk before lunch. We have Ed Page on deck, who is a member of the cargo team, maintains Clap, Winnow, many other things. I'm sure he can tell you all about them later. And he's going to give his talk, Performance, We're in This Together. Please make him welcome.
So first I have to say that with the career field I chose, I never expected to be presented on the silver screen. So that's quite an honor to be there. So when I put this idea forward, this was like, oh, this is just going to be a small presentation to the project members. So I didn't really put too much thought into it. That's a very ambiguous title. What kind of performance are we talking about? Well, when I proposed this was to the all hands. This was for us what our performance we're presenting out to the user. So this is actually about build performance, about how fast can we make builds, how can we make things better within Rust and the overall ecosystem. So overall, performance has been getting better in Rust. There's been lots of really great improvements. There's been lots of just small incremental optimizations done over time. There's been incremental compilation. There's been pipelined builds. There's been parallel backend. Those have all done a lot of good work to be able to make things faster. Unfortunately, that is not enough. When Rock was looking at their rewrite, they decided to switch from Rust to Zig, and it was because of the compile times. If you want to have more discussion on this, Richard is actually right over there, so maybe he can be part of the QA afterwards. People aren't needing just 1 or 2% performance improvements. People are needing to have orders of magnitude performance improvements. But there's also one problem with this quote from Richard. The fact that as somebody who uses Zig actually pointed out that Rust actually has better compile times than Zig right now. So Richard actually clarified that this isn't actually about Zig's compile times right now. It's about the fact that Zig has plans to dramatically improve their compile times, and he trusts them to actually deliver on it. Before Rock was even started, we've been talking about the crane lift backend. We're still talking about the crane lift backend. That's not to rag on the crane lift effort in of itself or any of that kind of stuff, but just how are we reflecting on how are we doing as a project and be able to build trust that we can actually make those dramatic improvements and be able to deliver on them for people. And it might seem like, okay, lock for lock, line of code for line for code, we might be on par with C++. That might be a reasonable thing to be able to say, and that's a good place to be for performance. Except that there's non-C++ developers out there who are wanting to use Rust for various reasons, and the bar is set much higher for them, ridiculously high, so high that it doesn't make sense for us to actually match it, but that's where the expectations are at, like, say, the Python users for the Astral people. And also, even for the C++ developers, if I'm writing a game using the Unreal Engine, am I recompiling Unreal every time I do a make clean make? No, I'm only remaking my own things. But if you're using Bevy and you do a cargo clean cargo check, it's rebuilding Bevy. And so there's just a whole different approaches being taken here that when we talk about, our build times might be on par with C++, that's not good enough. So what do we do about this? So to talk about that, we first need to make sure that we frame our discussions about performance in terms of the user and how this impacts the user. Us tracking performance is important. Us being able to see these 2%, 5% performance improvements is important, so we also don't have the opposite where we slowly degrade performance over time and not realize it. However, this is not how the user thinks. The user is reacting to the performance. If things take too long, they might go and they might just be annoyed if it's taking longer than they notice it. Or they might be like, okay, this is taking a bit longer. Maybe I'll go check things on Reddit. Oh, this is taking longer. Maybe I'll go for a coffee break. This is taking a really long time. Maybe I'll just start working on another project while I wait for the results for it. So you find that performance measurements for users are discrete, and there are huge orders of magnitude between them for what reaction the user gets. Because even if you make it like 10% faster within one of these workflows, the user is still off doing something else, and they're not going to notice because they're distracted with something else. You've lost their attention. And so you need to make it so you can make things faster such that you never lose their, that you bring their attention back into a smaller area of losing their attention. But what kind of user reaction, what are the users reacting to with this, that they might be going through these different stages? Well, this is about the user's workflow. What is the user doing? They might be iterating on errors and warnings, lints, making their code nice. They might be iterating on a test, getting it working, getting the results they want from it. They might be doing some exploratory programming, or they might be waiting for CI. And then one that's completely unrelated to us, they might be waiting for a reviewer, and that might actually end up being the real tentpole in this whole situation. But we also have to keep in mind that we have to dig deeper into each individual one of these, because it's that benchmark I was showing you for Rusty was for if you make an edit to a leaf crate, how long does it take to rebuild that leaf crate? Well, if you look at Zed, the text editor, they have over 150 workspace members, and their dependency tree goes about 9 deep. So if you're making a change to something 9 levels deep, how does that? What's the build times of that bubbling up through the rest of the stack for incremental compilation or for other things that you're doing? And so we need to be thinking in performance not just in terms of the simple, easy to measure cases, but we need to talk to users about how all these things are interacting with each other. We also need to talk to users about what problems they're running into with all this, because it turns out like one of the problems that Zed was having when we were talking with them was sometimes it just everything rebuilds. And it doesn't matter how much you improve incremental rebuild retime if you're also rebuilding all of your 1,000 dependencies. And that's because Cargo and Rust Analyzer were fighting over some settings that they had, and it was a suboptimal case in Cargo's caches. After a conversation with them, I went and fixed that so it was less of an issue. Another issue you run into when talking to people about this is they're usually jumping around in different parts of a workspace. They might be making a change in one spot and be like, oh, I need to make a change over here also as part of this whole effort of what I'm doing. And they'll have different features activated for all their dependencies, and things will get rebuilt again. Woohoo! So no matter how much we speed up the compiler, if we're doing these full rebuilds, it's not going to make much of a difference. So we need to look at the overall workflow and what all problems people are having through this whole process. So we need to talk to users. We need to have these opportunities to do this. Like that was really great that Nico set up that call with Remy and I to be able to talk with the Zed folks, the Rock folks. I'm pointing to the same people because I didn't realize they're the same people, and others to be able to hear about these kinds of problems that they're having. What's going on in their workflows? What's things slow? It's like some of the questions we brought up with them, some of the things I expected to be a problem for them turned out to not be. Like there's different work problems because it's like there's incremental builds, but there's also, well, CI, depending on your caching, you might get full builds. How much of a problem is CI? How much of a problem is this? Being able to iterate through those kinds of conversations was really useful. And when talking to users, one of the things that's important is to ask them, what are you avoiding? What is it that, or what are you working around? Because this is an example of, MacClad was giving ideas on how to improve your build times. And he was just like, abandon doc tests. Don't even use doc tests. They're just too slow. Well, that's a great thing to be able to dig into to better understand why they feel that that area is slow, because that could be a rich area for finding optimizations. And that's exactly what Guillaume did with the 2024 edition, where it's not just 2 or 5% performance improvements. This is orders of magnitude improvements in times. This is changing how a user is reacting. I mean, looking at that GIF time going from 4 minutes to 7 seconds, that is dramatic. So that's that's what we need to be looking at, is having those conversations about what are people avoiding, because you might miss things if you don't have those kinds of conversations. When inside the project, when we have these conversations, we also need to not be afraid to go out into the ecosystem. This is something that was really inspirational to me from Nick Nethercoat up over there, where he was trying to optimize declarative macros, and he just hit a point where he couldn't find any more optimizations. But he looked at the ecosystem and found that they're more algorithmically, people are writing macros that are more algorithmically complex than they needed to be. And he was able to just identify a few declarative macros within the ecosystem. They have improved those. They dramatically improved the build times for a whole bunch of crates, because a whole bunch of crates depended and used these declarative macros. And so we need to not be just afraid looking at how we can improve performance within the Rust project, but how are people using it, and should we actually be trying to find ways to be improving things in the ecosystem, just core load-bearing crates to be able to make it so we get this benefit everywhere. Actually, I forgot to also mention that he didn't just improve those macros. He then went and updated the little book of macros to have it talk about these trade-offs. So that way it'd help people in the future writing new macros to be able to improve the situation. So in all of this, there is areas that we could be able to have where the potential improvements are unexpected, where things might be indirect, where one team might have something that's kind of in their backlog that they've been kind of meh about, but there might affect another team in a way that can dramatically improve a user's performance. And we need to have conversations to be able to be aware of these kinds of things. For example, if Teeling was able to move forward with a implicit mod statements, that could actually improve performance. That might sound like a really strange thing. This is just a usability feature to reduce some clutter from code. So why does that improve performance? Well, back to that MatClad blog post, one of the things he talks about is when you write your tests, your integration tests, you put them in individual files, but then Cargo will build those as individual binaries and link those as individual binaries. And so you're now linking 20, 30 separate times, and link times can be dramatically slow. Granted, I before said be careful about what you're avoiding. So this might be also one of those cases where, hey, it'd be great if we improved link times. They're working on improving link times. There's things to improve link times even more in the future. So maybe this is one of those cases. But what MatClad was recommending was to combine everything into a single integration test binary. But when you do this, you have to manually mark all of your test mods inside of your main.rs. That's just annoying to do, and it's error prone. It's very easy to accidentally leave out one of your test modules, and it just never gets run, and you don't realize it. So it's hard to be able to recommend this workflow to users, say in the Cargo book, or to try to find different ways to try and push people towards this if people have to manually be specifying all of their modules. Again, I'm not saying necessarily that an auto mod type of a feature is saying hey, I'm just kind of doing a backdoor passive aggressive way of saying, hey, Teeling, you need to be doing this. But it's just to be able to say, this is an example of something that we can do where there's these indirect effects, where maybe we should consider this more than we might have otherwise, just because it has these effects on how people are behaving and how we can be able to take advantage of that. Another kind of surprising one to think about, probably a little bit less so than that last one, is there's a feature called config version and config accessible, which allows you to conditionally compile your code based off of what version of Rust you're currently using. And these can affect performance because there's many crates out there that want to be able to conditionalize themselves off of these things for being able to lower their MSRV. And in doing that, they're pulling in build scripts, they're pulling in proc macros, and it's slowing down your build to have to build those. There was a blog post, I think it was a week or two ago, where somebody was just frustrated, where it's just I had to just 5 dependencies to create this web server, and transitively I had 1,000 dependencies and was doing all these horrible types of things. So I went and reproduced his situation, and that was actually one of the things I found in that situation was they had, in their dependency tree, they had two different crates in the dependency tree for getting the Rust version. One of those used a proc macro, and then the other one was set up where you had to write your own build script on top of it. And so there's just this propagation of all these build scripts and proc macros through the project that dramatically slow down the build times because they're having to be linked, they're having to be executed and all that kind of stuff. That if we just had these one or two features, we could cut all that back and be able to improve their build times. There's also some other terrible things, like they had 2 separate copies of requests in their dependency tree, but that's a whole separate topic from this one. And a similar story for other features, like there's a config alias RFC up right now, and that was another thing where when I was looking through some build scripts recently, I was finding that that was one of the things that they're spending a lot of their time in their build scripts was just setting up all those aliases. Not that that's complex logic that's going to slow in of itself, but just the time it takes to build and link all of the build scripts can really slow down everything else. Another area that's important for us to be considering in the project is when there can be competing improvements. Where if we do 1 or 2 improvements on their own, they'll work great. But if we actually do them both at the same time, they might actually cancel each other out and waste a whole lot of effort and frustrate people. So I'm going to just run through a couple of examples that highlight different aspects of this. So proc macros, I've already mentioned, those can slow down your build for various reasons. But there's some improvements that we can be able to do to these. There's a PR up right now for caching the results of the proc macro being expanded. There's also been some more hand-wavy brainstorming of, what if when you do cargo publish, it actually snapshotted the expansion of the proc macro and was able to cut all of your proc macro dependencies and just be able to move along like that and be able to fully cache it and not have to build anything. That would be amazing. Or what if we're able to stabilize more features so we're less reliant on third-party crates that take a long time to build so that we can be able to then do even more things, be able to improve performance even more. That would be awesome. And also, proc macros, just to be aware of, have some other problems. We don't really have good input tracking for proc macros to know when rebuilds should happen because they can do anything on your system. They can go talk to a database. Yeah, that's a fun one, which, talking of, they're running arbitrary code, talking to databases, going to the network, doing all sorts of things. And they also lack a feature of declarative macros called, that's just the syntax is $crate, which allows you to say, for the code, for the API I'm generating code against, let me know how to reference that inside of the code I'm generating. So there's some downsides and trade-offs to proc macros. But one other avenue of this is Josh has some RFCs up for improving declarative macros so that you could be able to use them in the place of derives and attributes. Places where you'd use proc macros today, maybe you could actually use declarative macros. So if we could have those derive and attribute declarative macros, that'd be great. But they're difficult to work with. We'd need to be doing other things like improving some of the pattern matching so we can easily match a struct and be able to do different operations on a struct. And this also solves some of those problems that we have with proc macros today. They don't have the $crate problem. They don't run arbitrary code. We are able to track their build inputs because they don't run arbitrary code. So there's some really good advantages to taking this approach. There's also some ergonomic problems. That's understandable. But this could probably replace 90% of people's proc macros to the point that you could actually reasonably have a project where there's no proc macros running in the entire project. That would make a huge difference. But I'm also really curious about an experiment that Amos is doing, Faster Than Lime, where he's actually working on a generating reflection information so you can be able to introspect on the what your struct or your enum or whatever else is doing and be able to then perform runtime operations based off of that. So no metaprogramming, no code generation is being done with this, but that can still offer a lot, has a potential for a lot of really great applications. The main limitation is it only helps you with the use case of declarative macros. It doesn't help you with attribute macros or function macros. And you can't necessarily do some of the same kinds of compile time transformations that you can do in a proc macro. You can't necessarily take a field name and case convert it so instead of underscores it has dashes. That way you can use it and have a properly named command line flag, unlike some places where they use underscores instead of dashes. That always rubs me the wrong way. But this is an example where we could have multiple competing avenues. Like, yes, we could do all of these. That would be amazing if we could just improve everything and that'd be okay. But that takes a lot of time. That takes a lot of our focus. There's especially core teams that this depends on, like say the Teeling, where just they have limited time for being able to even work through some of the decisions that have to be made for some of these to be able to move forward. So we need to be able to talk, focus, and prioritize on what we're working on so that we can actually make forward progress rather than just being so distracted that the teams that we need to make decisions are constantly context switching between all these different proposals we're trying to push forward, and everyone's moving forward like inches at a time rather than us be able to work together to be able to move forward more dramatically. Another example of this problem with unexpected competing needs is caching. there's interest within the Cargo team, for being able to have cross workspace caching. People hack this together today by just saying two projects, hey, use the same target directory. And then occasionally they run into problems with that, like binaries overwriting each other and so on. But if we actually had a more native support for that, where we could actually better track everything that's going into that shared cache and handle everything coming in and out of it, that'd be great. And maybe we could add remote caching for this in the future, so that way you can go to a Cargo, say you're going to contribute to Cargo, you can say, I trust Cargo CI, and automatically download things from its cache and use it. And you now have access to, when you do your git pull, you can then also have it automatically pull things from the cache, and you're just all of your dependencies have been built already on this Cargo CI, and you can just get up and running and immediately go. That would be amazing. Granted, there are issues with build scripts and proc macros that we'd have to figure out through all this. We might actually have to skip those in the first version of this when we get it out. And another problem is, if you have a group of dependencies, so say you have a proc macro and a new version of Sin comes out, and you have two different projects with proc macros. They have different versions of Sin, but everything else is the same. But that basically creates a whole new entry for everything above Sin for the cache. And so there's a lot of reuse things that you run into with this. Like maybe there's a kind of a concept I've been playing with called opaque dependencies, where it's like you can say for a subset of your tree, like go use all the same version of your dependencies like use, say, clap, like use clap's lock file, keep it all consistent. Like if you use one version of clap, you get all the same versions of all the proc macro stuff, and you're good. And that doesn't affect me. So that way you can have better caching between different kinds of dependencies. And note in this, I'm talking about caching of things that are built. I'm not talking about pre-built packages. That's something that people are quick to be able to say, like, oh man, that'd be great if there's pre-built packages like that you see on PyPI or in other places. Well, that's because there's differences here. With Cargo, there's an expectation of transparency for within the top level application that has full access to control everything for its transitive dependencies, that it chooses, that the top level application can choose what version is used for anything, or patch out a transitive dependency and say, I actually have a bug fix for my particular application, or something my specific project needs that needs to be slightly different. You also have the different scenarios, like if something's pre-built, you have no control over what profile is used, and if you want to pass special Rust flags, you can't do that in that kind of a scenario. But when you're on PyPI, you're in a scenario where, well, you're all in Python and that's all in C, like that's all opaque to you. That's all hidden from you. You don't see those no matter what, whether it's pre-built or not, so you don't care about those kinds of details. And again, that's maybe where like the idea I said of opaque dependencies might be useful, is like, well, maybe we can like say all of this is shoved off and hidden from you, kind of like say Python pre-built packages, and maybe that could be able to help in the situation, but that's a whole new concept that we'd have to work out to be able to get there. But talking about any of this kinds of caching work that we might do, there's another concept that's been floating around that's mirror-only rlibs. So you can think of the compiler split into two parts, front end and back end. And mirror is, I believe, the communication layer between these. Feel free, any of the T-compiler people, to correct me in any of the things I say wrong in this part. And so what mirror-only rlib would do is, instead of performing the front end and back end for every single crate as you bubble up the stack, only do the front end work and save that off, and then in your final application, it takes all the front end information, all the mirror, and then does the code gen all at once. This has a couple of advantages, because back end can be really slow. So if you can reduce the amount of stuff you send to the back end, you can speed up your builds. And there can be situations where if you have a vec usize in two different crates, that'll be sent to the back end twice. But if we do mirror-only rlibs, that'll then be sent to the back end only once. Similarly, this allows an extra form of dead code elimination. If there's something that has code gen performed on it, but it's not actually used in the top level application, we will now no longer do that code gen. And there's actually a step further from mirror-only rlibs that we could be able to do. The Zig has a compilation model where they'll do, I think it's approximately generating an AST, and then they stop for all of your dependencies. And then what they'll do is they'll take the entry point of your application. So if it's a binary, they'll take your main. If it's a library, they'll take all of your pub items. And they'll just recursively descend from there, only doing generating effectively the mirror and then eventually cogen for only the things that are actually reachable from your entry point. And if we have any of these kinds of models, we're basically talking about doing a lot of the compilation process at the very end to be able to make that faster. But if we have caching, we're caching the stuff that happens before that. And so if we're reducing the amount of stuff that we're caching, if we're reducing the amount of work that we're caching, we're losing a lot of that benefit of the cache. And caching can come with an overhead cost. And so if we did both of these together, would we actually basically make it so the cache is useless and we just waste a lot of time trying to work on that? That's why it's important for us to be able to be coordinating and figuring these things out, so that way we can make sure that we don't have two teams working cross purposes from each other. Oh, hey, that picture did not load. I wonder why that's broken. Oh, I think I actually forgot to commit that to my blog, the fun thing about doing things locally versus online and forgetting to git add. Hey, that's another plug, JJ. You should probably use it. I'm not using it, and that's probably my fault. So this is supposed to be the picture of the beam of the guy where he's just like, and there's like all of the threads everywhere of like the things he's trying to map out. So I don't know how much it fully came across, but as I was talking about these things, it's like trying to track, here's this project, and here's this project, and here's how this thing might affect this thing, and this thing might affect this thing, and how this team is doing this, and this team is doing this. It's complicated. Hey, that at least is up there. And we need to unravel all of these threads so we can be able to figure out what direction we can even go in, to be able to make it so we can actually commit to people about, hey, like, yes, we can't fully commit because we don't want to do death marches. We want to make sure that we don't burn people out and all that kind of stuff. But people can actually trust us to be able to deliver on things. And so we need to talk to each other within the project. And as part of that, this talk is really a primer for my all hands session at Saturday at 9:30 to make so that way, one is, hey, make sure you know to go to it, and then two, make sure that we have some of the background set up for it so we can be able to get started in talking about this. And there's a lot of ideas of things that we could be able to do. Again, the huge screens make it so these kinds of things are not as overwhelming as you would expect, but I actually don't even have all of my ideas up here because there's some things more smaller down, focused on cargo, that are improving performance for some very specific workflows, but it's a pretty good sized list. And so yeah, we need to also be able to hear from you all about what ideas you have and be able to add that to the list and see how we can be able to coordinate on these things, be able to help things, how we can be able to change users' workflows to make things faster. And also, I can't do all this myself. Even all the things in cargo I can't do myself. I'm right now, my focus, well, I'm getting myself distracted again. I should be working on actually improving cargo test, but I'm distracted by a performance thing that's not on here. Once I'm done with that, I'm going to be focusing back again on cargo test, so I can't do this. We need people to come in, step up, and be able to help with these things. Like one of these, bottom middle is faster dev profile. Find a way to be able to broke the Gordian knot about the fact that the dev profile is both meant for iterative development and it's meant for debugging. And a lot of times those two workflows are actually separate, but we're slowing down people's iterative development in case they might at some point use a debugger. There's a lot of things that we need to figure out about backwards compatibility and all that kind of stuff to be able to split those things out. We need help, and people, it's not that it's going to be necessarily a hard problem, but we need people to actually just think through these things and consider the corner cases. So we need a lot of help to be able to get any of this moving forward. So if you're wanting to dig in and be able to make Rust faster, here's a lot of great ideas to be able to do so. And thank you very much.
All right, so Saturday, 9:30, no shortage of things to talk about. That is lunch. So lunch is downstairs. If you have allergies and you registered allergies when you registered, please ask at the first bar closest to the entrance, and we will see you all at 2 o'clock. Okay, welcome back from lunch. Mine was delicious. I hope everybody else's was as well. This is the Rust project track. If you do not expect to be in the Rust project track, please maybe vacate a seat for someone else. Turns out they're under some demand. So, welcome back. We'd like to first acknowledge the sponsors Aleph Alpha and Tandem Drive. Both of them have booths downstairs. They look like they're doing some pretty cool stuff. Please go talk to them if that seems interesting to you. I also have a note to, again, tell you all to defrag, but I don't think there's any point now because I think we've done the best we can, so good job, thank you. Our next speaker is Ralph Jung. He is an assistant professor at ETH Zurich, learned Rust 10 years ago, got into the Rust project by working on Miri as part of a Mozilla internship, and I'm told maybe a secret master plan 8 years ago, and is now a maintainer of Miri and a co-lead of the OpSem team. And he's going to talk to us about MiniRust, a core language for specifying Rust. Please make him welcome.
Yes, great. Mike is also working. Yes, thanks a lot for the introduction and thanks all for coming. I didn't think I would ever give a talk about formal semantics in front of a packed movie theater, so this is great. Though there have probably been more exciting movies played in this room, but fair enough. Okay, so specifying program semantics. Turns out that's a hard problem. And to demonstrate why that's a hard problem, I want to show you a little example. So here we have a little bit of Rust code. There's some unsafe in there, but there's a safety comment, so don't worry about it. And so we get an integer from somewhere, and then we just test something very innocent on the integer, because I called my mathematician friend, and they told me that every integer is less than 0, or equal to 0, or greater than 0. And so clearly, that should be true here as well. So we can just go ahead and run this code, if I find the right browser window. And we run this code in the latest stable compiler, and maybe I need to make this bigger, or maybe not with this screen. And it turns out that the assertion fails, as you can see here on the right, which is a bit strange. I guess now I need to call my mathematician friend and tell them we discovered a new integer. We don't yet know what it is, though. So let's figure out what the integer is. And let's just add a print here so that the compiler tells us what the strand integer is. And it turns out the strand integer is 0. And also, if we look at it, the error goes away. So maybe I need to call my physicist friend instead, because this is clearly some sort of quantum thing, right? Okay, what the heck is going on here? And by the way, if you try the latest beta that will be stable tomorrow, same thing. So what is even going on here? Well, there's kind of two options of what could happen here. This could be undefined behavior, which is like when you're breaking the rules of what you're allowed to do in unsafe code or not. And as we all know, with undefined behavior, everything is possible. So there's always a possible answer. But of course, it could also just be a plain old compiler bug, right? Like, who knows if the compiler is actually doing the right thing on this program. And so how do we find this out? Well, we go read the specification, and it should tell us. So yes, there is no specification. That is in part why I'm standing here and giving this talk, because I have some opinions on how the specification should look like. But we are kind of stuck here on the Rust side. So let's do the same thing again, but using a different programming language. So this is basically the same program, now written in C. And we can do the same thing again. Now we go to the demo, and it opens in the browser, hopefully. And we take the latest Clang compiler, and again, Clang also discovered a new integer. I had to make it a little bit more complicated here to trick Clang into doing the right thing, or the wrong thing. But in the end, you can see that also here, something really weird happens. And so same game as before. This might be UB, or this might be a compiler bug. And this time, we can go read the standard and find out, because C has an extensive standard. So let's do that. So here's the program again, kind of crammed into 4 lines. And so let's see what we can find in the standard that might be relevant to this program. So first of all, we find somewhere in section 6 that where we just have a local variable and we don't initialize it ourselves, the initial representation of the object is indeterminate. Okay, now we have to figure out what is going on with indeterminate representations. Section 3 tells us an indeterminate representation is an object representation that either represents an unspecified object or a non-value representation. Okay, so we have 2 more words we have to figure out what those mean. So if we go search for non-value representation, there's somewhere, we are back in section 6 now, but different part of section 6, where, well, certain object representations do not represent a value of the type. And if we do something with them with an L-value expression, that's what we call a place expression in Rust, that does not have character type, then something, something, something. Also, such a representation is called a non-value representation. So in our case, our L-value expression has a character type. It's not an accident. I used signed car here. So this shouldn't apply to us, right? This can't really be a non-value representation in that case, hopefully. Though we can also go look for more hints of whether that could be a non-value representation or not. And somewhere else in section 6, we find that, first of all, signed car does not have any padding bits. And we also find, as a non-normative note, but still potentially useful in interpreting the standard, that one way to get non-value representations is to have some sort of wrong padding in integers, because like some machines have integers with like parity bits or something like that. So this is how you could get a non-value representation. But signed car doesn't have any padding bytes. So like hopefully, I guess maybe it doesn't have non-value representations. So let's just assume it doesn't. So the other thing that it could be is an unspecified value. And what the standard says about unspecified values is, well, that we have a bug, and also that it is a valid value of the relevant type where this document imposes no requirements. And I mean, surely there's no valid value of that type which violates that equation. I mean, that's at least what my mathematician friend told me. So this must be a Clang bug, right? Well, if we dig even further, we can find further hints. At this point, we might feel like detectives in some sort of weird crime scene. So we can find some defect reports from more than 2 decades ago, where people asked about this part of the standard. Some of the terms are different here, because at that time, it wasn't called an indeterminate representation. It was called an indeterminate value. But so what the answer to this defect report says is that these indeterminate values can change if you look at them multiple times, basically. So it's a valid value, but it's like not always the same valid value. And the implementation, another part of the answer clarifies, is allowed to treat indeterminate values as being different from any other value, even though the standard also says that they are valid values. I don't quite know what that means, but the typical interpretation of that is that we kind of think of x kind of being unstable, and so each time you look at it, you get a different value, and that's how you can kind of violate this assertion. So I guess that's the answer then. So if you look at the IR that Clang generates here, it actually gives this program full UB. There's like a no undef annotation somewhere. So I don't think that is backed even by that part of the standard. But this aside, just figuring out the behavior of this program, what are the legal outcomes of red from the standard is really, really hard or nearly impossible. You kind of have to dig into these old defect reports, which are not normal, like they don't apply to today's standard. This is a defect report for a 2-decade-old standard. The standard hasn't really been changed in that regard. So this is really tricky. And to be clear here, I don't want to throw shade on the C standards work here. They are doing an amazing job at something really hard, which is a very advanced form of cat herding, of getting a whole bunch of compiler developers and implementers together and kind of getting them to agree on many things, which is non-trivial. And they did many things right, and they have this extensive standard, much more detailed than what we have. But they also made some mistakes, which is not too surprising when you do this kind of work. And I would like Rust to ideally not repeat those mistakes. I think we can make our own new and fun, unique mistakes. So that's what this talk is about. So when we get to a Rust language spec, there are some desiderata I would like to propose we should kind of measure. We should expect the spec to have or to be successful. And in particular, I would like it to be precise. There should be like in some mathematical sense, there shouldn't be any room for ambiguities in the specification. So we don't have to do this kind of guesswork that we just had to do interpreting this other program. And actually, I would go one step further and would say the spec should be executable. So over the past decade or two, there has been a bunch of academic work specifying complicated real-world systems. For example, we have a very detailed machine-readable formal specification of a very, very large part of the ARM instruction set architecture at this point, actually generated from the official ARM documentation. It's really impressive work. And one of the lessons we learned as part of that is these specs themselves, they're huge artifacts, and we need to be able to test them. Because otherwise our spec is going to have bugs, and then, I mean, what do we do with that, right? So we need to be able to test them, and for that we need to be able to run them. Just take an example, and here's the expected output, and just make sure the spec actually says what you want it to say on these examples. And that's also super useful for tons of other things. You can use if you have a question like the example program we had earlier, you can just ask the spec, and it gives you an answer rather than having to read the spec. You can use it as an oracle for fuzzing. Like if you come to compare if your compiler is correct, just generate a whole bunch of random programs and see if it says the same thing as the spec. Executable specs are really, really valuable. And so I think this is an absolute must for a proper spec these days. But also, of course, I would like the spec to be accessible. I mean, we can, like, I'm an academic researcher. We like writing our papers with lots of Greek letters and weird lines in them. And they are amazing, but not many people can read them unless they did a PhD in programming languages. And the Rust spec is something, I mean, Rust unsafe code authors need to be able to read that to be able to write Rust unsafe code. So we can't have that be full of Greek letters. Right? We need to find some way to make this precise and executable while also being accessible to at least reasonably well-experienced Rust developer. I wouldn't expect like someone who's just starting to learn Rust to be able to read this. That's okay. I think it's okay to expect some amount of Rust understanding, but it's not okay to expect a PhD in programming languages. So this is what I'm trying to achieve with this project of mine called MiniRust. It is a core language, we will see what that means, that can fully capture the runtime behavior of Rust programs. And the style of the system is it's what's called an operational semantics. We'll also see what that means. Expressed in Rust-like pseudocode. We'll also see what that means. So let's start with an example. Here's a very, very simple Rust function. It can't be much simpler than that. And here's the same function in MiniRust. So those of you that work on the compiler, MiniRust is very much like mir. So should be easy to parse in that front. We have a function body which has a list of basic blocks. Every basic block, a list of statement followed by a terminator. And then whenever we access a local variable, because a local variable is a place where you can store some data, you need to be explicit about what do you want to do with the place. Do you want to load from it? Do you want to store to it? So the typically implicit in Rust place to value coercion is made explicit here. So we load from X, we add 1, and then we store the result in the place on the left-hand side of the assignment. The return value is stored in dedicated return place, which is just another local variable whose name is given up there. By convention, I'm using ret here. This is all kind of fake. MiniRust doesn't really have actual syntax. You can't write MiniRust programs in syntax like that. But I'm just displaying the syntax of the language like that. So to understand what MiniRust would say about our initial example program, first thing we have to do, of course, is translate this program into MiniRust. Now, literally translating that would give us way too much output, but we can use this program here, which is almost the same. So what does this program do? Well, we have a local variable i8, and then the first thing we do is we storage live it. So this is the moment where we just have a local variable i8. This local variable doesn't actually yet have any memory, because by default, local variables are dead. And so this is how we model kind of scopes, right? A variable that only actually exists in some part of the function. So we enter the scope, we call it storage live, and this is a bit like malloc or Rust allocate for stack variables. So we do that, and then we do the comparison, and I've now replaced the short-circuiting OR by a non-short-circuiting OR just to keep the code a bit simpler here. But this is basically the same check as what we did before. And then we jump to different basic blocks depending on the result of the comparison. Okay, so we've seen some MiniRust programs, but those were concrete examples, right? The point of a spec is to say in a finite form something about all possible examples. So we need to find some way to do that. We can't just list all the programs. And so we need, first of all, of course, a proper exhaustive description of the syntax that to even define what is the set of all MiniRust programs. And then, and that's the crux, of course, a description of the runtime behavior of some arbitrary MiniRust program. So to describe the syntax, this is what I would do if I would put this into some sort of PL paper. This is probably not too bad. I mean, some sort of BNF grammar is actually fairly widely used also outside of hardcore PL research. So I would expect many of you would be able to kind of understand what that is. But still, let's already start thinking about how can we make this as accessible as possible to this specific audience, you all, Rust programmers, without losing the precision that is kind of implicit in using some sort of mathematical notation. And so what I'm going to do is I'm just going to simply write Rust code. Or Rust-like pseudocode, which is a subset of Rust. So instead of saying a basic block is like statement with a line, semicolon, term, you just say, well, a basic block is a list of statements followed by a terminator. You can think vec whenever you see list, but I want to keep it a bit more abstract here. And then a terminator is like one of these things, and then we have statements and we have expressions, and you can just describe all of this, basically describe the abstract grammar of the program as Rust data types. So this should be abundantly clear to everybody who's learned like a few weeks of Rust. It's just very basic Rust data types, right? Probably just after the first week already. So basically in terms of the syntax, we are done because we don't actually care about a concrete syntax. Right? We don't need a parser or anything like that. We only need to represent the concepts of the program. Okay, so now we get to the interesting part, which is describing program behavior. So there are various different kinds. If you went to some lecture at university about operational semantics or so, there's various different kinds of ways you could express program semantics. And what the C standard does is what I would argue is some flavor of axiomatic semantics. Not exactly the typical axiomatic semantics, but it's some flavor of that, where basically the standard gives you a whole lot of reasoning principles which you can use to argue for the correctness of your program. And then if you want to say that my program is fine, doesn't have UB, you have to find sentences across the standard which you can chain together to make an argument for why your particular program is fine. And that has various downsides. I mean, we've seen already it can be hard to even find out where you have to chase those sentences across the standard. It's very, very hard for a compiler to argue correctness of an optimization against such a specification, because you kind of have to be like, okay, give me any program that was somehow proven correct by chaining together these arguments, and now I have to think about what I can do with that. But this is super hard, and it's not really how any of the formal approaches for compiler correctness work. And it also can have accidental side effects. I mean, C famously added provenance to their standard, and then 20 years later they realized that they did that. Because it's very easy to add some rules which talk about things like pointers being derived from other pointers or so, and then later you realize, oh, this actually has profound consequences that affect all of the rules everywhere, and it wasn't accounted for. So I think there's some major downsides with this side, which is why I think in Rust we should go for an operational semantics, and it seems the project agrees because we have an official operational semantics team. So this part is kind of already done and decided as far as Rust. So what's an operational semantics? Abstractly speaking, for an operational semantics, we define a state space and a step function. I'm going to make this put this more into Rust terms in a minute. So what we would write formally is we first describe our state space. So that is kind of all of the things you need to remember to describe the current state of how far you've executed the program, right? The value of all the variables, the contents of all of memory, everything. So mathematical notation would look something like this. And then we have a step function, which tells us from one state, how do you compute the next step? How to execute one statement or whatever granularity of step you might choose. And the funny half arrow means that this is a partial function, because a step there can be no step, right? This is a program which has UB. It's often modeled as just you can have no step here. But again, this is mathematical, and if we would start out writing those functions, we would get into Greek letter territory very quickly. So let's avoid that. Let's use Rust syntax. We can just define the state space as here's my struct, and here are the pieces of the state. Here are the things I need to describe the current state of program executions. And I mean, Rust has functions, of course. So if we want to write a function which computes the next state, we just write a function that computes the next state, and it's a partial function. We can do this in Rust. We have this fancy thing called option. And so what this is, you might recognize, is it's basically an interpreter. Right? An interpreter somewhere has all of the state that is needed to track like what is the contents of everything, and it has a function you can call to do one step. Or usually it's in a loop and you just do the entire thing, but you can imagine just extracting the one step thing into separate functions. So an operational semantics is basically just a mathematical version of an interpreter. So what we're going to do for MiniRust, we're going to give it an interpreter. And so I can't go over the entire interpreter here, but I want to take a slightly closer look at this memory type, because that's where some of the most interesting stuff happens. So the memory from the perspective of MiniRust, and now we get into choices I made, some of which are kind of just modeling existing consensus or already decided things, and some of which are just decisions I made so that I have a proposal for what MiniRust could look like, and there's going to be discussions on what the final version of that looks like. So we have the address space of the program. Let's assume a 64-bit machine, and just spread across the address space, we have a bunch of allocations. The spec doesn't care about stack or heap or globals or anything. Every allocation just gets some address randomly, non-deterministically, anywhere in the address space. And more importantly, the contents of these allocations are, well, they are the bytes stored inside the allocation, and those bytes are a bit funny, because those bytes can be either the bytes you all already know, standard just initialized to some particular value, or they can be uninitialized. We consider this to be just another value a byte can have. So there's explicit tracking in the interpreter state, which is just the spec, of which bytes have been already initialized and which have not. So this is, of course, a picture. This is not precise and unambiguous. So let's make this precise and ambiguous using the tools we have. Memory is just a list of allocations. An allocation has an absolute address and a list of bytes, and a byte is either initialized or uninitialized. And so even these interesting, non-trivial concepts here of what is a byte are very easy to express in Rust, because Rust has enums, which are amazing. And so every Rust programmer understands what these few words here mean, and we've very precisely described a very non-trivial aspect of our semantics in a way that is accessible to everybody who did at least a week of Rust. And so one thing you might also notice looking at this in particular, if you are someone who thought a bit about the C or C++ specifications, is there's no types here. Like, types are very important in Rust, and somehow they are suspiciously absent entirely from this view of memory. Because in this model I'm proposing, types don't actually show up in memory, they show up when you do stuff with the data in memory. So more specifically, types are or define how values as like abstract mathematical high-level concepts are represented in memory. The way we could think about it is there's some enum of types. I won't bore you with the details. You all know the Rust type system. And then there is an enum of values, which is in particular includes things like mathematical integers. Right? At this point, the number 260 is really just the mathematical number 260. It's not like a sequence of bytes or Indianness or any nonsense like that. And like a Boolean is really just a mathematical Boolean. A tuple is just a value for each of its fields. Like, this is a high-level view of the value. There's no bytes anywhere here. But of course, in Rust, we store values in memory and we load them out of memory. So we have to somehow bridge that gap. And to do that, we have two functions. There's an encode function where, given a type, if you have a value, it constructs a list of bytes. And that's basically just a form of serialization. Right, we're given the number 260, we're saying our format is I32. Okay, I know it's a big endian system. Here's the 4 bytes that get out of that gets turned into. And then, of course, there is a function which does the opposite. Right? Whenever you have serialization, you also have deserialization. So those two functions together define this abstract concept of like how does a high-level value get represented as a low-level list of bytes. And crucially, decode can fail. Right? It returns an option. So some representations, some sequence of bytes just don't parse. They're just not a valid representation of any high-level value. So if we want to discuss our example now, we will get into, well, there was a type I8, is the type I used there, right? So we want to answer the question of what exactly happens when we decode an I8 from its representation. And so slightly simplifying here, we're only given a single byte because I8 has size 1. And we have to write this function. And so, of course, the first thing you do is you match on the byte, because what else could you be doing? And now, we defined bytes earlier, right? There's two cases to handle. Either the byte is initialized. In this case, well, I mean, there's a bit of stuff going on here. We have to take the byte and do the 2's complement to get the mathematical integer. Details don't really matter. The point is, this is something you can define. And everybody agrees on what should happen there. More interestingly, there's also the uninit case. You can't just forget that, right? If you didn't write this, Rust would just not compile this code, and neither would our Rust-like pseudocode. And what we do is just return none. I mean, we could also say return 0 or something, but that sounds pretty bad. So we just say, yeah, if the byte is not initialized, then this is just not a valid representation. And so knowing that, let's get back to our example program. And let's see what happens when we run this program in the MiniRust interpreter. So the first thing that happens is storage live. At this point, we create a new allocation that backs the memory for x. And initially, well, it only has a single byte. And that single byte is initially, of course, uninit. That's the entire point of this uninit special magic value. And then we go to the next line of the program, where we load from x. And so what happens, where we take this uninit byte and we pass it to the decode I8 function we just saw. And that function returns none, which is an error. And so at this point, the specification says we have undefined behavior, because whatever you did there, whatever you gave me there in terms of memory, is not a valid representation of any I8 value. So in the spirit of being executable, I can show you this as a demo. So here, no, I want to increase. Here we have, again, as a Rust file, just the program that I used. And if I run this in Minitest, our caching isn't perfect, so there's a bit of rebuild going on. And then first of all, we see that the Rust compiler is way too smart and already recognizes that something's wrong with the program. But then at the bottom here, we have the output from the MiniRust interpreter. This is not the most beautiful output. The interpreter is not meant to be as a user-facing tool to find bugs in your code, right? It's meant for us to find bugs in the spec and to do conformance testing and things like that. And we will work on improving that, of course. But nice error messages are like the last priority in this particular project. It's not Miri. But the key point is that we could just run the spec, and the spec immediately told us unambiguously what is the answer to the question of what happens when you run this program. And the answer is it has undefined behavior. Okay, so beginning to wrap up here, we've seen how the MiniRust formal specification, which is basically an interpreter, is able to precisely capture why this program has UB. And roughly the high-level structure of MiniRust is that, first of all, of course, we have to translate the Rust program into MiniRust. The details of that are TBD. Of course, at some point, we need to make that formal as well, and we will think about that at some point, but not yet. And then we have a MiniRust program. We have the MiniRust interpreter, which is written in this Rust-like pseudocode that is called Specker. And you can think of it as basically a purely functional subset of Rust. And you can just run that as you just saw in the demo, and it'll tell you what the program does when you execute it on the specification. So I have a bit of time, so I want to show you at least one of these aspects here of MiniRust, which I find interesting, or one of the consequences that happen. So one of the types, of course, we have to define is bool. So this is the decode function for bool, right? Again, bool has size 1, so we take a single byte. If the byte is initialized to 0, then this represents the mathematical Boolean false. If it's initialized to 1, mathematical Boolean true. Everything else, not a valid representation of a bool. And so one of the interesting things that happens here is that if you try to parse like 55 into there, you also get none. Right? So all of these things, which we often call invalid representations, that's also kind of defined as part of this. So if you go to the reference, and there is this section there on like it's UB to construct an invalid value, then we list there, well, a bool must always be false or true, 0 or 1. And this is already captured as part of this, right? So the main goal is to define how do representations relate to high-level values, but actually as part of this, we are implicitly defining the validity or the language invariant of the type. That invariant isn't actually a part of the semantics, it's just a derived notion from the fact that some representations are not valid. And for all the others, we have to define what the value is, and then if we have a fallback case like this one, we just say, okay, everything else is invalid. And I have one more here about padding. So this is the idea here is if we have a type, like let's say we have a pair with 2 fields, and there could be padding in between those fields, how do we encode and decode that? Well, what happens here is for decoding, we just subslice the corresponding 2 parts of, like we get a large area of bytes, and there's like 2 subslices which correspond to the 2 fields. We just decode them, right? What else would we do? But in particular, this means if there's padding between the 2 fields, it gets entirely ignored by this decode function. It's not even like the value we return here, the pair, doesn't even have that padding in it. It's just lost. And then when we encode, we start with an array full of uninitialized, and then we just slap the 2 encodings in the 2 places. So there's an interesting quick quiz question here, which is if we start with a whole bunch of zeros, right? We have 4 zeros, and then we decode that and encode it again. So we round trip from the high-level value to the low-level representation and back. At this type, I8, I16 with a defined field layout. So there's a byte of data, then there's padding, and then there's 2 bytes of data. What happens? And the interesting thing that happens is that the padding gets lost, because when we decode, we just get the mathematical tuple 0, 0 as a high-level value. And then when we encode that again, all of the padding is reset to uninit, right? Because the fact that there was 0 in the padding is not even represented. So these decode-encode round trips can be lossy, and so these representation relations also implicitly define the fact that padding is lost on typed copies, as we say. The encode-decode round trip, by the way, has to exactly preserve the value. That's important. Okay, so the MiniRust interpreter, again, the goal is to precisely capture for any program, whether it has UB or not. And I should also mention that this is worked by much more than one person. I have a lab now, so I get to assign students some tasks, and they will happily do it because they get credit points for it. So a whole bunch of people worked on various aspects of MiniRust. In particular, Rudy did all of the work of making MiniRust something you can actually execute, not just a whole bunch of markdown files. And then a sequence of mostly bachelor students added a whole bunch of Rust features. So at this point, we are fairly close to covering most of Rust. On the other hand, of course, there's still a long list of things we don't have. I don't know if we will ever get floats. Probably at some point, someone will get nerd sniped into doing that. But there's lots of intrinsics we need. And to make this practical, to test the spec on slightly more interesting programs, we also need to do some engineering things. And of course, we want to make it formal. another connection to the rocks prover, or to Nico's mere formality project. So there's a lot of work still left to be done. Yeah, I would like to add the at least moving towards 100% coverage emoji to the list. And there's one final emoji I want to add here, because currently this is my project, my research project, and it will stay like that for a bit more because I need to complete it first. But I hope long term we can all work together to make this part of the official specification for Rust, to make it authoritative. That's what the final emoji is meant to represent. Because in doing that, we would make Rust, to my knowledge, the very first language that of its level of complexity, a language that has undefined behavior programmers have to worry about with unsafe code, that actually has a mathematically formal spec officially in its standard. And I think that would be an amazing thing for us to do. So thanks a lot.
Thank you, Ralph. Okay, we have a few minutes for questions. Wow, okay. I'm going to go this way.
Thank you very much for your presentation. My question is, you showed this really nice operational semantics with the step function. In the state that you presented there, the state struct, you also had a list of threads. What happens when threads are introduced in this model? Because then you have some non-determinism there, probably. So does the step function turn into something more complicated than going from state to option of state? Or what happens there?
Yes, yeah, very good question. Yeah, so the language spec is non-deterministic, and I cut out the slide that explains that for lack of time. So the short version for the experts is we do a monadic representation of non-determinism. So the slightly longer version, well, the slide is cut, so I can't really show it. But basically, in the so Specker is a language. It's a purely functional subset of Rust, and it has one or two really extra funny operations. And one of them is pick, which is a non-deterministic, which is meant to model non-deterministic choice. It's a function where you basically give it a type, and you say, give me some value of this type. Slightly more refined, you give it a type and you give it a predicate, which is a function from the type to bool, a closure from the type to bool. And the pick function is specified to just be non-deterministically return any value of the type that satisfies the predicate. And so when we execute the spec, of course we can't, so nominally what happens is kind of the program branches every time you use pick. And all of these executions now could happen. And if we did a formal proof, we would have to worry about all of them. Of course, when we execute the spec to test it, we will just pick one at random, because that's the best we can do. It's an easy word. You could imagine some fancy symbolic things or whatever. But basically, we have this very special magic function, and we call it in the spec at all of the moments where we want to model non-determinism. And then the executability is slightly degraded there, but the mathematical rigor is still there. If we translate this into a formal model in Rock or anything, we can use an actual accurate model of non-determinism. And yes, I mean, it's a bit less accessible because it's a weird magic concept, but non-determinism is something we will need. So I think this is a reasonable, and also it's formally a very common way of exposing non-determinism in a specification like that.
Okay, I think there was just one over here.
So you showed that in MiniRust a byte is either an init or an integer value. Where is the provenance?
I removed it for this talk.
Okay. Thank you.
Yes, I didn't have an hour, so yes, there's of course also provenance actually in those bytes.
On the subject of pointers and references, if memory is bytes, how does that at all? How do you enforce the aliasing model?
Yeah, the answer is provenance. So again, it's something I didn't get into explaining here, unfortunately. But a pointer is not just 64 bits. A pointer is a 64-bit address plus some magic extra metadata called provenance, and that's the high-level-ish mathematical value of a pointer. And then of course you need to be able to encode pointers into memory and decode them again. So we also need to enrich bytes with provenance to be able to round trip this. And then using provenance, we can basically track which pointer got derived from which other pointer, and we can use that for the aliasing. So the MiniRust that I just executed, I showed you, it has an implementation of tree borrows already inside of it. So it does do all the aliasing checks.
Okay, I'm very sorry to the other 45 people or thereabouts who had hands up, but I am sure Ralph will be very happy to talk about this later.
Definitely.
We are unfortunately out of time, and so thank you again to Ralph. and we'll be back in 10 minutes for the next talk. All right, welcome back to the extremely unpopular Rust project stream. Thank you all for coming. Thank you all for being here, and thank you all for squeezing in as best you can. From a talk where types were irrelevant to a talk where types are doubly relevant, Ollie is here to tell us about adding pattern types to the type system. Ollie has been a compiler team member for 7 years, worked on Rust full-time for 4 years, and tomorrow marks 10 years since Ollie's first const eval contribution to Rust. So that's very exciting. A few things happening tomorrow, as it turns out. So please make Ollie welcome.
So this talk is going to be initially just a quick intro into pattern types, but then I'm digging into how it's actually implemented in a type system. I think it should be generally understandable, but just ask questions afterwards. Lots of questions. So quick intro. What the heck are pattern types? Well, they're basically types that are not the full value range of their original type. So if you have like an integer like u32, you can limit it to like 1 to 100 or something, and can dump a value in there, and it will just work because 12 is obviously between 1 and 100. But if you try something else, you get a weird compiler error because this feature is not meant for public consumption. This is literally there to make the compiler easier. Yeah, use it, but only use it in a compiler, please. There's also one interesting part, that is pointers. Pointers can be not null. Anybody ever seen a bang null pattern? No, because it doesn't exist in patterns. I just hacked this in so we could replace the non-null type in the standard library. Yeah, before we ever get this to anybody outside of the compiler, we'll have to have a long discussion with the Lang team about that one. So the correct way to initialize one, you just saw I did it with a bunch of numbers, but what if the number is out of scope, or you want to have a runtime value? The compiler can't check runtime values, so transmute. It always gets you all the right values unless you do UB, so that's bad. So what's the better way? The better way is you match on the value. If the value matches the pattern that you gave, you do all the unsafe code here, converting this to a pattern type, and otherwise you get a none. This is a nice macro that I just added for myself to the standard library, so stuff would be easier. And the previous implementation that we had like all this complicated code for ensuring that like a range pattern is like the value is like below the range, above the ranges aren't like overlapping, going the wrong direction and stuff. And now it's just like match on a pattern. It's so much cooler. So the actual best way would be if we had like language support for doing stuff, but like not part of this talk, because this talk is not about actually doing cool language stuff. Sorry, this part is about compilers. So compilers. What do we actually want from pattern types? If we declare a pattern type like this one, we know it only has valid values from 0 to 100. So this u32 has a lot of bits that are unused. And we can use those bits. The compiler is using those bits. If you've ever used a non-zero, non-null value and you stuck it in an option, it was the same size as the option. Same thing works here. You have the size of %. I don't know what the size actually is, probably 4. And this size of the option of % is the same size. And this stacks. This is the same size as the original %. And the size optimization is really useful, especially if you're doing like interop with other languages which have like non-null values like randomly everywhere. So if you want to use like nice options and stuff, that's really helpful. So why did I start all this work? Well, why did I start implementing pattern types? It's not just for a cool feature or something. It is for replacing whatever that long attribute is. I keep forgetting how to write it. Like I literally had to go look it up to write it in this thing, even though I've been using it everywhere. This attribute is a compiler internal hack to change the layout of this struct, even though internally it has a u32, to tell the layout of this struct to be like, well, except for the value of 0. Oh, except for the values below 1, but that's for unsigned integers, that's 0. And this attribute, it was a pain. Because if you now access this integer and just write a list 0 to it, that's UB. If you take a mutable reference to this integer and send it to someone else and they write a 0 to it, that's UB. And there's like a billion other ways to make this UB. And we made this sound, which was a lot of code, just for an internal compiler feature. So my hope is pattern types will take less code, and currently it's looking at least at it's more maintainable, not necessarily less code. So I want to replace that one, the non-zero u32 in libcore, with just like a struct that wraps a u32 as one dot dot. And now you're actually allowed to reference this field in there, and everything is fine because this type, you can't do anything with it. Like a pattern type right now in the standard library that you use, it's like, it has no fields, it has no methods on it, it has nothing. So all you can do is transmute it back to u32, because sometimes you need to get a u32 out of a non-zero u32. But that's already the case for non-zero u32. It's like when you're using it, you only have a bunch of methods on it. You never access its fields. The field is private anyway. So for all users, this doesn't actually do anything interesting. So done with the intro. Now we're going into compilers. So I try to add pattern types as like the syntax where you say like u32 is one dot dot to the language, and immediately somebody's code broke because somebody wrote a macro that internally writes like tie and then followed by an is, and then my parser was like, but that's already a tie, and then everything broke. So we had to stop doing that. We'll probably do it over an addition, or we find a new syntax, but we're not trying to do that. So what I added was a macro to standard library that has a lot of compiler magic here. But it's basically just these two things where tie is null or tie is pat, and then the compiler figures things out. And by figuring things out, I mean the parser is literally like, check if there is a bang after the is, and then require that as a null, or just parse a pattern. And so we either have a pattern, like you saw here, pattern, or we have a null. And then we stuff all that back into an AST representation. So you already know patterns that you use in macros all the time. They have like all these different variants, but pattern types, they don't really know that much. They have not null, they have ranges we've seen, and if or. We'll get to or later. But like we are really trying to limit what you can do with pattern types for now, and we're treating them as a completely separate concept, and we might merge them back together again at some point, or make stuff generic. But for now, we're keeping it a completely separate code path that we can just analyze and exhaustively match, and everybody's happy on that count. So when we parsing, I said we parse a pattern. So we get a pattern. That's a normal pattern that you see everywhere, and we want to turn that into a type pattern because, well, we want to have the simpler representation. So basically, we're just moving values from those dot dots to those dot dots, and the or does the same thing. And we don't even have not null because they don't exist in a normal one. As I showed earlier, we just handle them as separate code path, and everything else just puts out like a really not helpful error. At least the span is nice. I took some effort in making span nice. Yeah, it's not on the level of diagnostic that we would ever want, but it's usable for inside the compiler and inside the standard library, so that's good. Now, that's the AST. I have to move this into the type system. So how does this actually look right now? When I started, I had a range pattern, and a range pattern has a start. But it not necessarily has a start. It only sometimes has a start because you can just write dot dot 5, which has no start. So there's a none for the start. And then there's a constant because you could be writing one dot dot. So for that, there would be a constant here. You could also write like named constant and so on, but like that's fine. The end has the same thing, and then we have an include end because you could write dot dot equals or dot dot. And this representation just represents exactly how we would represent it in the AST, because that's how ASTs works. They just represent what you're writing. In the type system, this has a bunch of problems. So when you have a U8 is 1.100, you have a sum1 for the start, you have a sum100 for the end, and you have like this, is the end inclusive, which is no, because there's no equals here. But look at this one. This one, these are like the same. And like, but they look different because this one has a sum99 and has a true here. So we have the same type technically, but differently represented, which is fine in the AST because the AST just should represent what you're writing. But in the type system, these two types are the same and they're not the same. That's bad. And so initially I was looking at like, how can I make this better? Can I like figure out how to make the type equality checks, like figure out, oh, if there is a true here, then I need to add one to this and compare to that. And then, well, let's simplify. first simplification, let's get rid of the options, because those are already a little bit annoying. So the AST doesn't change. What we're changing is the representation in HIR and in the type system. And so whenever you see a missing start or end, you look at the type and just insert the right, well, start or end. But at the place that we're doing this, we don't have type information yet. So we need to figure out how to ask the compiler to later fill in the correct value here. And earlier I already showed you that we have constants here. And constants, they can't just be integers. They can also be projections into traits. So what it was in the standard library, I declared a trait that basically had max and min values for all kinds of integer types and for characters. And so in the lowering from AST to HIR, I see, oh, there's an option. Well, just rip out the option, take the type, because we're saying like the U32 is some pattern. The U32 we have available, so we just generate this whole U32 is my super weird fancy trait, : max, or min, depending on which range we want. And that allows us to change these to at least have no options anymore. So you see it doesn't run out of my screen anymore. That's good. But we still have the dumb thing of like this Boolean here that makes us distinguish between equal types but unequal types. So the next step is, how can we get rid of this difference? How can we just get rid of this Boolean once and for all and have this kind of representation? I mean, this is super easy to represent and to understand and to equate, because we can just equate the start and the end, and if there's a difference, then they're different. There's no more logic that you have to put there, but you have to figure out how to get the end properly stuck in there. And well, we have subtraction, I guess. So if we represent this one, which doesn't include the end, as 100 minus 1, that works actually pretty nice. It works for integers at least. Then we can represent all these values. It's basically a tuple of 2 integers, and the type system is fairly happy with this one. Well, right? Well, the problem is you still have ranges that people can specify, like, let's say 10 to 5. So runs out of the back and comes in from the start or something. But yeah, that might be doable if like people actually write numbers. But what if people write generics? How do you do this here? Like, I could write something in compiler that literally checks like the constant value, but like in this case, there's no constant value. This is something that will get filled in later in the type system. Like, somebody will insert an A and a B, and they could be inserting them in the wrong order, or somebody could have flipped the order of the generic parameters here. So we need to figure out how to actually compare the range ends here. And the good thing is we don't need it for our standard library stuff. So now I'm extending beyond what we would need to actually change the standard library to get rid of those weird super long Rust C attributes. But now we're getting more into stuff that we can do in the future and be working on. And so remember I told you about this trait that has like this min and max, and it also has a weird function for sub1 because I needed to subtract 1, and it was very hard to write out like how to subtract 1 in the compiler. So I just made a function call because that's easier. But with characters, it's even worse. So if I want to subtract from characters, how do you subtract 1 from characters? Like, I can't do -1. So I converted back, where are we? There. The sub1 function itself, it converts the integer, the character to U32, subtracts 1, tries to convert it back to character. In case it doesn't work, gives you a panic. And in case it works, it gives you the value. And diagnostics on that are surprisingly good. Like, this works pretty well. But the problem is, if you start using this in generic contexts, you still have to somehow call the sub1 function. And if you've ever used like the const generic expression stuff, it does not like it if you like do things that panic. So yeah, we'll need to do something better here. So initially I was thinking, let's just scrap char and like let's like look at integers, but then I looked at integers and they were like, oh, that's just the same code. So has the same problem, obviously. We're thinking a little bit more about how to do this properly, and so here's a bunch of examples that I will go through one by one, and then we can think about what the problems with them are. The first one, we have generic A and B, and we just compare them, and B is inclusive. That's easy. We just convert them to A and B. We put those into those constants. We say constant start is A, constant B end is B. Everybody's happy. Now, if we stop using equals here and say like B is not included, that means we need to subtract 1 from B to do our nice representation thing. And that means we now have this inside a constant. So there's a method call here that could technically do anything and could technically panic, and it will actually panic. So we need to take care that this doesn't panic. And well, I'll leave that to the next person holding a talk here, so we won't talk about that one today. Here you can see if we're just going to one value and leaving out the first one, this one's pretty easy. There's a constant here. It's we're just projecting into that one. That's completely fine to do. So what is actually the problem with the one up here? I need to skip over a slide, sorry. The problem is we need to make sure that all our types are correctly represented in a type system. So we need to, at any time, be able to check, is this type actually valid at the current position? And usually you do that by looking at your where bounds, or you're looking, if you don't have any where bounds because you're completely monomorphic, you just don't have to do anything interesting. But we want to do all of this in generic code. So when we have a function like this, function true, ignore that one up there, we need to check that this U32 is actually smaller than 10. And there is like 3 different ways to do it, and they're all equally like icky. So we're looking into how to do that one best. Right now, the compiler actually correctly handles this. If you have all these features turned on, and some of them are like incomplete, so you get warnings about incomplete features, this will actually error with an error that doesn't actually show you where the error is from. This is all the error that the compiler spits out. And we literally cannot do better than this. At this stage, that's part of the problem of the whole generic stuff. At the point where we know that something is wrong, we don't have any information left to actually tell you where it went wrong. So the only way to do this is to know at the signature of the function foo where something went wrong. So when we're declaring this function foo, we would somehow have to extract this pattern types information or add some where bounds here that declare that this A must be smaller than 10. And that's the entire problem that we need to solve to make pattern types actually work. So to get further with pattern types, we first have to do a bunch of lower level type system stuff around const generics to get somewhere interesting. Right, so what solutions do we actually have? We can generate some implied bounds or something where we see like, oh, there's a pattern type in the signature. So the compiler could generate magic stuff that you can't write yourself. But that breaks down when you're only using a pattern type in the body of a function, because now you can't say that bound anymore. You could add like dummy where bounds and so on, but it gets really annoying. So maybe there are other solutions. We could have like an untyped integer type that's like a big num in the type system that you can't actually put into the normal into normal runtime code. But that it has its own problems because untyped is not really something that Rust does. So we'll have to find some better solution than that. And then we could special case just pattern types to be able to work around these limitations we put there on purpose out of good reason. Because if you're looking at like arrays, like you can sometimes declare arrays that fail in the same bad way as this one, where you just get like a one-line error that says this array is unfortunately too large for your platform, and it changes between platforms. Yeah, we want to avoid that and make it better. And yeah, we're looking into all of those solutions, and we're trying to figure out one way to make it better, and might take multiple ways. But for now, standard library is getting easier, compiler is getting easier, but the feature itself needs a lot of work and a lot of thinking. It's not actually needs a lot of implementation work. It just needs really a lot of like thinking work how to do this correctly. Yeah, that was me on pattern types and the compiler.
I appreciate that you've left us on a cliffhanger for the next talk. Okay, questions. I feel like there'll probably be a few. Okay, I am going to come that way to start with.
I should have brought sunglasses.
Hi, Ollie. How bad would it be just not to support open ranges?
Not that bad. It's just you could just say we always need inclusive ranges.
Yeah, sure.
And since we're also thinking about just never allowing floats for pattern types because those are also annoying. So if we're already limiting, we could limit it more. That would simplify a few things. Correct.
Would that be useful enough?
It would avoid the subtract one issue, but it wouldn't avoid the flipping, where you have an A that's larger than a B. And in that case, like we need to do it anyway. So there's no like on top of that check, it's not that much more.
I see. Thank you.
Could you
Okay,
say
here.
that empty ranges are just empty instead of being not well formed?
Empty ranges are just empty instead of not being well formed. Oh, yes, we could do that, but that's different from what pattern matching does. So we don't want to invent too many disconnected concepts. We want to try to make pattern matching and pattern types at least like not have disjunctive features. They are allowed to not have all the features of each other, but like at least not like, well, pattern types are supposed to be a subset of patterns, basically.
And I guess riffing off of that, is the range 1.1 just not well formed, or is it the never type?
1.1 is an error. You can't write that as a pattern either, so we're actually erroring out on that. You can write a pattern that is only a single value, though.
There was somebody up here, a couple of people up here. All right.
I was wondering with the when the use case is already just super limited, you have to transmute. Why the effort of making like those patterns that are logically the same, actually the same in the type system? Why not just keep them separate and then save the sub1 stuff? And
so the main reason for that is that in the type system, I want it to be simple anyway. Like it is not to support all of these use cases. I could have just removed it from the syntax, so that the AST is not allowed to represent it either and error it out at that stage. That would have worked. But in the type system, I want to have the simple type system that I can actually reason about and explain to people like what's going on instead of just hoping that I did everything right.
I was wondering, could you for now limit the pattern like start and then to just be literals instead of like supporting all of those constants? Because to me it seems like for what the standard library needs and for what a lot of people would use this feature for, just having literals instead of any arbitrary constants would be more than enough.
So differentiating between literals and constants at the type level, there's no difference anyway. So I would only have to make the difference at the AST or the HRR level, and at that point, I don't think we gain that much. Being able to specify like a constant somewhere that declare the limits of your type and not having to repeat the things or use too many macros is what I tried to allow. The previous system with the attribute, it was very, very limited. It only allowed literals, but yeah, it didn't cost anything extra to just allow constants.
I think as a remark, I think for the character type, you should skip the surrogate pair range instead of -1 because you can have ... the surrogate pair, the end of surrogate pair range. You should actually skip over the whole surrogate pair range instead of just -1 because that will panic.
Right. If you're right, that would actually be the more correct implementation for char. You're right.
All right, I know there are a couple of people down the front. Give me 1 sec to come back down without breaking an ankle. Okay. Okay.
So somebody commented about floats earlier, and I know that there are a lot of people who want to apply this to float types for things like non-nan, non-infinity, non-zero. They don't necessarily need full ranges, albeit they might want non-negative, for example. But I'm wondering if that makes it any simpler. And in the broader case, like you talked a lot about integers. Could you talk a little bit about like the enum case, the more general pattern case of, you know, I have a this that is only this variant, that kind of thing?
So with floats, the answer is very simple. We don't have that in patterns. If we're not able to match on it, then we're basically not. And we're basically not adding it there. But at that point, yeah, it would totally be possible. And with all the problems that we have with floats and const generics in general. You saw the OR pattern that allows you to specify separate ranges, and one of the ranges has to match. And you could use that to match on enums in the future, where you create an enum that is only a subset of the actual enum variant. A result that's only error, or the case we have inside the compiler itself is we want to exclude some types, some type variants in specific locations because we know they can't happen anymore. Yeah, there's definitely a lot more space for adding more features to pattern types, but that's less implementation work and more talking about what we actually want from it.
Just quick question about the ABI representation. Does this work? Does it affect at all the internal?
It affects the layout, but it does not affect the ABI itself, in the sense that you can always transmute a base type of a pattern type, like a U32 to a U32 that is any other range. You can always do that in both directions, and it's the same in function signatures, so you can just change it in function signatures as long as you're guaranteeing that everybody's sending the correct values, obviously. But yeah, it has the same ABI that's not actually being touched. No.
Okay, do we have anyone else?
Hello, yeah. Would it make sense that instead of like specifying the type directly, you would define like a magic trait that contains like this magic associated type that is implemented only if the actual pattern is valid, has a valid range? So you hide the actual pattern type behind something like a magic associated type.
Well, right. So you're declaring basically a trait that has the range ends as generic parameters and has an associated type that gives you the pattern type.
Yeah.
I'm not sure that would actually solve that much. We could specify all of that in the signatures and so on. So we could basically bubble up the subtractions and all the way up, but
yeah, because with this, then you can specify this in the where bound. So if it's a const generic AB, so now you require that this range AB to implement this pattern trait.
Right. That would absolutely work. I'm just pretty sure it's not the kind of signature that people would want to write. I mean, it's similar to like you can basically do this with type num. Which works. It solves a lot of these problems because it's just completely in the type system, but it's also like very verbose to write.
Okay, thanks.
All right, I've been told we have time for one more. Yep.
Are there plans for, or do you have a status on taking this data and putting it in MER, or is that already done?
So this is part of the type system that flows into everything the compiler does. So MIR and MIRI and everything, they see these values. MIRI is checking how non-zero and non-null types work, and this doesn't change any of that.
Yeah, cool.
Well,
thanks.
Famous words, because the PR that's implementing that is breaking MIRI. I'm fixing that.
All right, sounds like there are many questions and a lot of discussion on this, but that's all we have time for now. Please say thanks again to Ollie. All right, Rust project trackers, welcome back. We are completing our trilogy of type-related talks where we've gone from no types to all the types with a talk from Boxy. Boxy is on the types compiler and release teams, part of the Const generics project group, and co-created the unfair Rust quiz, which my notes say you should all try. I actually tried it yesterday because I saw the notes yesterday. It really was unfair, so
Yeah.
I appreciate that. Anyway, Boxy's going to talk to us about the state of Const generics.
Okay. Okay. Wait, is the mic on? Yeah, I can hear myself. Okay, Const generics. So I've been working on Const generics for about 4 years now, and yeah, so back in 2021, when Const generics was stabilized, I started working on Const generics a little bit after that. So I had nothing to do with the original stabilization, but the original stabilization had a number of limitations with it. It didn't support all the possible use cases, it just supported the sort of minimum necessary stuff to just let you do basic operations with arrays, like storing them in structs and accepting them as function arguments while being generic over the length. But there was a lot that wasn't supported. We didn't support defaulted Const generic parameters. Unlike types, you aren't able to explicitly infer Const generic parameters. You can only implicitly elide the generic arguments, which doesn't come up a lot in practice, but it's still something we should be supporting. The set of types that we let you use in Const generics is limited to not very many. It's just the integer types char and bool. So I think the most common thing you use for this is just array lengths, because you can't really make your own types. And maybe the biggest limitation is that we don't let you do any computations involving generic parameters in the type system for Const generics. You're only allowed to use single generic parameters. So I'm going to go over each of them a little bit, what has happened with each of the features over the past 4 years. So the first one, defaulted ones, works exactly the same as with type parameters. This was stabilized at the end of 2021. I want to say it's the only Const generics feature we've stabilized since, but I'm not actually confident in that now that I'm up here. If there is one we've stabilized, I don't remember, and it's not in this talk, so that's great. I can't remember whose talk it was, but at some point in this conference, someone was talking about how features get pushed by lots of people, and Const generics is a great example of that. A lot of the people who worked on min Const generics no longer work on Const generics, and so there's a lot of different people now, and the people who did work on this, a lot of different people. The original implementation was Julian, LQD helped a lot, Varco did a lot of the reviews, and then myself and LCNR did a lot of the stuff towards the end. So that's stabilized, that's easy. The next one, this is the not being able to explicitly infer things. It's kind of hard to craft an example that doesn't use the expressions for constructing arrays, so I'm just using that because it's one of the only cases where you're forced to explicitly write out the length. So if this was if this was a type, you'd just be able to write underscore, but here we don't allow this on stable, and we would like to support this. This was difficult to support not because of design reasons, this was just difficult because of implementation reasons. It's a lot of stuff to do with the internals of the compiler. We wind up having problems where it's not necessarily clear if an underscore argument is a type or a const. In this case, it's clearly a const, but when it's more generic, just arbitrary paths, then it's not necessarily super clear. We've recently resolved that, so this feature is basically done implementation-wise, and I'm hoping we can stabilize this soon. Yeah. Again, those are some of the PRs that were sort of instrumental recently, and the profile pictures of some of the people who worked on it. Some of the same faces, compiler errors has helped. Camelid is somewhere in the audience, I can't see you. There you are. Indirectly helped with some of the MGCA work, which we'll talk later. The middle profile picture at the top was somebody named Void who helped with some of the refactorings recently. I have no idea, I've never seen them again. So that's that. This is about the different types of const generic parameters. We don't support this code. This is code that I would quite like for us to support, and we probably should be. It's quite a common use case to want to be able to write your own enum and then be generic over the different values. This feature had a lot of both implementation and design concerns. Implementation-wise, it was quite difficult because it's on here somewhere. The internal representation of how we represent values in the type system contained a bunch of superfluous extra information that we don't really want to care about or need to care about, and that made things kind of, you know. And the other thing is that deciding what types should be allowed to be used in const generics is incredibly non-trivial. I think Ollie talked a bit about floats. Floats are kind of annoying because the equality rules around them are weird, and we probably want stuff in the type system to have like reasonable definitions of equality, which floats do not. References are annoying in the type system because, Ralph, I don't think you talked about this, but they're really annoying in the optem because that you can just put whatever you want behind them, and so putting them in the type system is either we store a bunch of extra stuff that's not necessary in the type system and causes equality to be weird, or we sort of lossily delete the data from the type system and then stuff doesn't round trip properly, and that's also weird. So the current implementation, we've kind of conservatively just ruled out those things, and we'll maybe come back to it at some point. Oh, Ralph's on there. Yeah, I put that there. I think that's from a lot of the earlier work on vowel trees. Ollie's also helped a lot. You know the faces on there. Oh, Elsiana, you're on there. Okay. This is maybe one of the... I don't know if it's necessarily the most important limitation, but it's the one that I've spent the most time working on. It's that we don't allow you to use generic parameters in const generic arguments unless it's a bare parameter. This has been existing unstably under the generic const expressions feature gate for like not quite 4 years. There was a lot of renames. It started off as the just general const generics feature gate, then it got split out into const evaluatable checked, I think, and then we've renamed it to generic const expressions, which is where it currently is. This is a very difficult feature to support. There are so many design issues with it. There are so many implementation issues with it. And a lot of those problems came from the fact that the scope was really big. We tried to support every single expression. We tried to do everything with it. And recently, we came up with a design that's more limited in scope. So like how min const generics was a thing, we now have a minimum version, which I'm calling min generic const arguments. We've been working on this for kind of almost a year now. I think it was July last year that we came up with the design. Camilla, who I've forgotten where they are, they're over there, has done a lot of the implementation work on this. It's been a project goal for the past 2 project goals. The general idea is that instead of supporting all expressions, we're going to try and just support uses of associated constants and top-level const items. This means that all of the type system rules are equivalent to the existing type system rules for types, and we really have a good understanding of how those work. It's a very well understood area. We can just copy all the rules and we know everything's fine because realistically, const generics isn't actually that different from type generics. A lot of the difficulties we've kind of handled, like there was the way we represent values is slightly different and its own unique complexity, but it doesn't really have that much impact on this feature. So yeah, we have this now. It's not quite in a usable state yet. It's quite far along the phase to getting an MVP though. Maybe like 1 or 2 more PRs. Camlet has a draft PR to get to the point where, did I put it on here? Yeah, the bottom left one, that's Camlet's open PR currently. Once that's done, I think MGCA will be in a point where we can actually start experimenting with it. We can, yeah, if we can start experimenting, we can finish out the feature. When that's done, it's likely that generic const expressions will be able to be more properly implemented. I don't know if anybody's tried using it, but you've probably run into a lot of issues with it if you have. And when this work is done, we'll be able to sort of re-implement generic const expressions in terms of the min-generic const arguments design, which should hopefully work a lot better. So that's sort of all of the features that we are actually experimenting with. So I realize I forgot to say any of the feature gate names. That's fine, you can figure that out. So there are some things that we don't currently have feature gates for that are sort of often requested for us to experiment with, but we're not currently doing it. One difference between constant type generics is that if you have a type parameter, there's kind of an infinite set of possible arguments that people could call it with. We don't really have the concept of sealed traits in the compiler, so even if you can seal a trait and then only have a limited set of implementers, that's not really something we do anything with. So for this purposes, it's kind of like type arguments. You could have many of them. Whereas with const generics, there's a limited set. We know every single argument you could give to a bool, a const b bool. And so something that kind of arises there is if you have an impl and you're generic over a const generic parameter, sometimes people ask us if they can manually implement every single generic argument differently and then use the impls from a generic context where they just have some generic const b bool. This is very similar to specialization. We don't currently have a feature gate for this just because it's very difficult to support. I don't really know how we do it. There's a lot of, it would take a lot of capacity that's otherwise being spent on things like MGCA. And also just design-wise, it has so much overlap with specialization that I feel like we need more experimentation with specialization first before we sort of dive into a conflicting feature. And then the other thing we don't support that's often requested is people want to write bounds like where n is greater than 10 or something like that. The generic const expressions feature kind of lets you do this just because it happens to be really powerful and do everything, but it's not really a special bound. It's just you can do it because you can put arbitrary constants in the type system. And so something that sometimes come up is that people would like to just be able to write these bounds directly. And something that's kind of interesting about that is that we kind of already have a way to limit the set of values you can pass to a function. That's just types. So if you want to write where n is greater than 10, we don't have a greater than 10 usize type in the standard library, but we do have a non-zero type. So if you wanted a greater than 0 const argument, you could just use a non-zero usize if we supported that in const generics, which we will eventually. And similarly, Ollie's pattern types talk, you could see how there might be a connection there. How you could have a const generic parameter which was const n, and then usize is like 10 ... and then you get your greater than 10. I don't know how that, there might be a bit of a bootstrapping problem there if pattern types wants to use const generics to, I don't know, pattern types is hard. So yeah, we will probably come back to these at some point when there's more capacity and whatnot. There's no Lang team consensus on any of this, by the way. This is unstable experimentation that all needs to be stabilization reported and FCP'd and whatnot. So if there's anything you see and you're kind of concerned, or you're like, hey, actually I would like this use case to be considered, like there's still time, come find me. But that's the end of the talk. I don't know how long that was. It felt kind of fast. I maybe should have done more.
I am pleased to say that you are dead on time
Really?
to allow a little bit of question time. So,
Awesome.
Does anybody have questions for Boxy? All right, I'm coming your way.
So with const generics, one of the questions is we migrated a lot of the standard library types over from these macros with up to 32, but we left out the default, and I think 30 has a similar issue there, that they can't specify that the trait can't be or doesn't need to be implemented for the 0, right? Do you have a solution for that?
don't think I understand what you said. Can you say it again?
So with default and with the 30 deserialized and serialized, we have for arrays sized 0. We don't require the type T to be serialized and deserialized, right? And for anything which is greater than 0, we do require this, right?
Oh, yeah, right. So that's also a problem in the standard library. I think that might have been what you said. I can't remember what. It's default. Yeah, we messed that up with default. I honestly don't know what we're gonna do there. It's unfortunate because we kind of would eventually like, for example, default to be implemented for all lengths of arrays, and we currently can't do that because it's special cased for 0. Maybe that's a thing that's solved by some kind of specialization, but honestly, I don't know. It might maybe just work if we, when we support more kinds of const generic types, maybe we can accept like a usize that's greater than 0 and then somehow figure it out, but that kind of goes into the same thing of like this starts feeling like specialization, and it's definitely a problem that needs to be considered. But also, I don't think that thinking about this is something that necessarily blocks the other work. So it's something that I'm kind of trying to get the other stuff out the door because there's a lot of value to be had there. And then it's like, okay, how do we deal with this thorny problem that's kind of up in the air?
Thank you.
Okay, anyone else? Okay, all on the other aisle, of course. Run, Adam, run. Okay, put your hands up again, please. Right, perfect, you're in the same row, even better. Let's start this end.
Okay, I have a question about well-formedness. So I recall that it used to be the case where if you have generic const generic expressions, you have to put this weird unit array of certain lengths, and the length being the const that you want to use in a word bound, so that it implies well-formed. So I just do a quick check. It looks like this check has been gone. Is it moved to modifization time because we already have the array being too large issue, or what's the update on this?
Okay, so in generic const expressions, because we allow arbitrary expressions, they can panic post-monomorphization, so we get post-mono errors unless we try to design our way out of this problem. The current solution that GCE does is that we require all generic const arguments to be put in the type signature somewhere, so that the caller knows that this const argument exists, and then it can check if it's fully concrete, and then evaluate it, and then the error is no longer post-monomorphization. With min generic const args, by not allowing as many expressions, we sort of just know by construction that there's not going to be any issues post-monomorphization, at least nothing worse than types already have, which for the most part don't have post-mono errors except for some really fringe cases. It's one of the things that's nice about MGCA is it kind of, we can punt figuring out the sort of exact details of how we want post-mono errors to interact here. A full generic const args / when we rewrite GCE to be in terms of MGCA, that's a lot of acronyms, then we'll probably wind up with something there which is still, once again, a bit up in the air, but yeah, MGCA is free of that problem, and that's a big win.
Bit of a meta question. You showed an example with enums variants being able to be used, like you specify a const enum bound and yes, perfect. Okay. Yeah, that one. This seems, first of all, like a wonderful feature. Second, it seems like there's a significant design space both from an implementation perspective and also from like a what does this look in the language perspective. I'm curious what the process is for bringing something like this to real life, first in obviously unstable Rust and then eventually into stable.
So the specific case of const generics is honestly kind of weird because everything got RFC'd in like the big const generics RFC forever ago, and it kind of included a lot of stuff, and then only some of it was stabilized, and then all the stuff that wasn't stabilized stuck around as unstable features. I think it's not super unusual for us to experiment with unstable features just in the compiler without there being sort of a strong, I'm not sure what the word I'm looking for is, just kind of off on our own experimenting with features. It's not that uncommon. And then, so once we've sort of resolved all the implementation difficulties, we sort of know that like, okay, this is something we could actually support. And then it's like, okay, we need to hammer out all of the design space, and like that's sort of where like the language team comes in. So in the specific case of this feature, now that the implementation is like kind of getting there, and I'd say all of the sort of big problems with it have been resolved, the next step is like we need to like involve the lang team. We need to like make sure the design is good. I honestly don't know if it needs an RFC or not. It was in the original Const RFC, but there's been some minor divergences. But also the RFC was like 6-7 years ago, so you know maybe it warrants a re-RFC in general. I hope that answers your question. I just kind of rambled.
All right, that is all the Q&A we have time for, so let's thank Boxy once again. All right, we have an afternoon break for half an hour. We will be back at 4:20. Good job. Welcome back for the last block of the day. Before we begin, I'd like to acknowledge our sponsors for the Unconf rooms, Google and FutureWay. Those of us who are attending the All Hands and Unconf, I think particularly will thank them very much for that. Our next speaker is Predrag Grevsky. I only have one note for you that was provided by Tertz, which was to ask, you should, I don't think this is me asking, you should ask Predrag about the time he went to watch a giant rocket explode. That does sound like fun. Predrag is going to talk to us about what it'll take to eradicate unintended breakage from Rust, and let's give him a hand.
Thank you. It's a pleasure to be here. Like Adam said, my name is Predrag Grevsky. You might be familiar with some of my work on cargo semver checks and the trustful query engine that powers it. And right about now, you might be thinking, I didn't mention being on any Rust project teams, so what am I doing in this room? The answer to that question is that my work necessarily touches the work of many other teams. Definitely Lang, Cargo, Rust Doc, many others. And so as a result, I end up finding all sorts of interesting things in the Rust language, some of them intended and some of them less so. Like, for example, when adding an import can cause a major breaking change. That I don't think was ever explicitly designed into the language on purpose, but it is the reality of Rust as we have it today. I also write explainer blog posts because I need to deeply understand various features of Rust, like how does trait sealing work? Trait sealing is not a language concept, but it is a reality that many crate maintainers use. And so cargo semver checks has to support it correctly, or else it will just produce categorically incorrect results. It doesn't matter that this is not a language level concept. It is a concept that cargo semver checks needs to know about. So I'm here essentially as a consumer of the output of many teams, and also as an interface toward many of the maintainers in our community. Because when they run into issues, oftentimes I'm very curious to learn more, and therefore I have a very wide purview of what is going on in the Rust ecosystem, and I'm hoping to distill some of that in this talk. So the purpose here is to give you some intuition of what Rust looks like from my point of view, both toward the maintainers, the consumers of Rust, and also how the output of various teams in the Rust project looks to me. And with that, let's get started. I'll start off with a hot take. Unintended breakage is bad. It is a lose-lose proposition all around. Maintainers are in the frustrating position of having never made a concrete decision to break something to be responsible for the fallout. They have to triage the GitHub issues that get raised, they have to remediate the breakage, and oftentimes they leave their users stranded. Users also have a bad time. They never signed up for that breakage. They just ran cargo update and now their project doesn't build. That sucks. And this also sucks for every one of us as a Rust community, because it teaches us to not trust our tools. Cargo update is not fearless today. And that's unfortunate, because it means that we don't update our dependencies as often as we could. And so we don't benefit from the bug fixes, the hard-won performance gains, the security patches that get shipped, and so on. So we're all living every day with worse software. So unintended breakage is bad. Let's assume that we've decided to make it a goal of the Rust project long-term to eradicate unintended breakage entirely. What would that look like? That is the point of this talk. So the framing is very simple. Alice is one of our users. She runs cargo update. Her code stops working. This might sound like a hypothetical case. It is very, very much not. A cargo semver check study run across the top 1,000 most popular crates in the crate ecosystem in 2023 revealed that we ship, on average, about 1 to 2 semver breaking releases every week. More than 1 in 6 of those top 1,000 crates has shipped accidental breakage at least once. So this is a very real thing that happens even to the most expert maintainers. So this is the reality of Rust today. We might not like it, but those are the statistics. And more importantly, this is a study from 2023. This number is definitely an undercount, because cargo semver checks has more than 4 times as many lints today. So if we redid this study, we expect that number to go up, not down. Some assumptions and some ground rules for this talk. The first and most important one is we're not solving a security problem here. So everyone has the best of intentions. There's no malice. People are not breaking stuff on purpose just to be annoying about it. We're also not going to assign blame to anyone. We're going to categorically reject the concept of human error. So it is a bad system when it lets well-intentioned users down. But just because a system is bad, it doesn't mean that we're going to throw the designer of that system under the bus either. Every one of us here is doing our best. And we're all trying to improve how things work. And that starts by pointing out where systems could be better. So we're going to take the mindset of, here are the places where things need to be better, and let's figure out how to get there. We're not going to assign blame to anyone. And a bit of a meta point, we're going to say no shutdowns. So let's all adopt the mindset of, it could work if, not this will never work because. This is a very important and very personal rule to me, because when I was starting cargo semver checks, I was repeatedly told it will never work. I was told, we've tried this 3 or 4 times in the Rust ecosystem, and the project failed every single time. And so here's a laundry list of features why this will never, ever work. So it's just not even worth trying. Like, let's just save you the time and tell you not to bother. And yet, here I am, and here cargo semver checks is more than 3 years later. It's used by a vast fraction of the Crates.io ecosystem. So I think the news of its demise was a little bit overstated and premature. All right, so Alice has run cargo update and her code has stopped working. What this means is that some other maintainer, Bob, has released a new version, and something happened with that new version that when it got picked up by cargo update, the project broke. Okay, so let's play Sherlock Holmes a little bit and try to put on our detective hats and figure out what happened and how. There are a few different options. The obvious one is that upstream broke semver, right? So there is a major change. They got shipped in a version release that was not major. Cargo update picked it up, and now the project just doesn't build anymore. Cargo check just fails with some compiler error. The natural question here is, why did cargo semver checks not stop this, right? We would have expected that the maintainer ran cargo semver checks, and then they decided to move forward. And in order to understand this, I want to tell you a little bit about how cargo semver checks works. The idea here is that if we're going to release version 1.1, we want to compare the API against version 1.0. And if there are any breaking changes between those two versions, we want to flag them and say, hey, this version might not be right. 1.1 might not be the right version number. You might need 2.0. The way this works under the hood is that we will build the rust.json for the proposed version 1.1, and also for the already published version 1.0, and then we will compare them. So we will look for breaking changes between the two rust.json files. Just to give you a little bit of intuition about where time is spent, about 90 to 95% of the runtime is in actually building the rust.json files for us to inspect. And then less than 10% of the wall clock runtime is actually inspecting the rust.json files and looking for breakage. All right. To give you a bit of a sense of what these checks look like, here are some very real lints. So let's say a public function used to exist at some publicly importable path, and it no longer exists at that path. So that is clearly breaking because you can't import that function and use it anymore. Another example is a public function takes a different number of arguments than it used to before, so this is also clearly broken because any of the calls that supply the previous number of arguments will just not work anymore. We have about 140 other lints in addition to these, and the number of lints is growing exponentially. And when I say exponentially, I'm not exaggerating. It is quite literally exponential. It is doubling every year. So this is not a trend that will slow down anytime soon, and in fact, we're currently ahead of the curve for this year because we have hundreds of lints left to go. So broadly speaking, if there's a rule and we don't implement it yet, then try again tomorrow. The news might be different. So why didn't cargo semver checks catch our example of breakage? Well, there are two options, 80-20. Option number one is we haven't implemented the rule because we don't know what the rule actually is. Like, when is the thing that happened breaking? And option two, we do know the rule, but we don't have the necessary data. Rust.json or some other component just does not ship us sufficient information for us to have detected that breakage. We're going to dig into both of these one at a time. And there's actually a secret third option. Shh, don't tell anyone. The rule involves types. There's type-related breakage. This is not something we're going to catch today, and it's one of the surprising things about cargo semver checks. There's a good reason why we don't already have it implemented, but we are actively working on it. So if that's something you're interested about, please ask me later and I'm happy to talk about it. It's not a main part of this talk though, so I'm going to just set it aside for now. So let's just dive right in. Option number 1, we don't know what the semver rule is. In order to figure out what is the semver rule, we need to essentially rules lawyer a little bit and figure out what exactly might be broken and how could we possibly convince a user that the thing that we claim is broken is actually broken, right? So in an ideal world, we would have a concrete Rust program that we could show the user and say, this used to work and this doesn't work anymore, right? And so this is a breaking change within the spirit of RFC 1105, the API evolution, and other normative documents in the Rust ecosystem. The difficulty here is that Rust is a big language. There's a lot of things to think about. There's a lot of features and there's a lot of interactions between those features. And so this is much, much easier said than done. In practice, this is actually the hardest part of writing cargo semver checks lints, just figuring out what the lint should be, what should we catch. And there are 4 themes that I want you to look at as I show you a couple of examples of this in practice. One is that we need to do a lot of research. The rules are not written down. It's not like we have an exhaustive list and we just need to check a bunch of boxes. We need to figure out what those rules are. In order to figure them out, we need to do a whole bunch of experimentation. And in order to make sure that we get the right rule, we need to handle all of the inherent complexity in the Rust language. All of those interfeature interactions need to be thought about, experimented with, and researched. And then finally, there's a lot of risk. Because if we get this wrong, then bugs happen, both false positives and false negatives, and those are both bad, and we'd like to avoid them. So we really want to be right, and that requires that we be very, very thorough in this step. That's why this takes so long. So here's an example. I was recently looking at the target feature attribute. If you're not familiar with it, it just allows Rust functions to say, the following features must be present on the hardware where this function is running. And there are several different ways to use it. The details are not super important, but I'm happy to tell you more about it later if you're curious. And this is just me beginning to look into this feature and writing up essentially a lint report. These are the following things that we need to catch. These are the semver hazards and proof, how we would convince a user that something is a hazard and so on and so on. So this issue is the product of many, many hours of my work. As you can see, there's experimentation right there. There's a playground link. I wrote a piece of code and then I had to go check it in the playground to see if a thing that I suspected might be breaking was breaking or not. What I'm also not showing you is the many conversations that I had with people in this room to help me understand this feature, which obviously, is never written down in the GitHub issue, but I'm deeply grateful to everyone that helped me. This is the rest of the issue, by the way, because obviously it doesn't fit on one screen, even on this big one, even on this one big screen. And there are a couple of interesting things you might notice. One is that as I was thinking about semver hazards, which are necessarily some sort of inconsistency between different package versions, it turns out that you can write an inconsistency within the same version. And if you can trigger inconsistency in the same version, we call that lang unsoundness. We ended up, the Rust compiler ended up accepting a program that it should not have, a program that is self-inconsistent, that specifies different things in 2 different places. So this research was already useful. We haven't implemented any semver lints, but something good came out of this. Thankfully, this inconsistency is not something that's likely to come up terribly often, so we should be able to close that hole without making too much of a fuss about it. But it's still nice that we managed to find the gap and address it before it bit anyone. And the other thing you're going to notice is that after many hours spent on this, the issue ends with a list of open questions. And this is because I'm not an expert in this feature. Like, I spent many hours learning about this, but I'm still a noob. I've never used this feature myself in any of my crates, so this is just my best understanding of how things work. And that understanding is necessarily incomplete because I'm not the expert on this. And then after I wrote this issue, a handful of helpful folks jumped in and offered some suggestions, helped me close some of those open questions. And then there was more work and more discussion, and some more work and some more discussion, and some more work and some more discussion. And at this point, 0 lines of code or lints have made it into cargo semver checks. This is what I mean when I say the hardest part of writing new lints in cargo semver checks is figuring out what are the lints to write in cargo semver checks. That's why this is hard. When this process goes wrong, we get issues. Here's a false positive where cargo semver checks was incorrectly detecting that a trait was sealed. Now, trait sealing is a topic that is complicated enough that I would need a separate 1-hour slot to walk you through it. So of course, please ask me about it in the Q&A if you're curious. But in this case, we were categorically getting the wrong answer. We shipped an update to our trait sealing analysis, and it was just wrong. Within a month, 3 different projects chimed in and said, hey, you broke us. And it was wrong in a tiny little edge case. The fix was 1 line of code. We had more than 2,000 lines worth of test cases that were written prior to this, and none of those test cases managed to find this one tiny little edge case. But cargo semver checks is deployed so broadly that one tiny little edge case broke 3 separate projects within a month. So that's the risk that we're facing. That's why it's so important to get this right. So the thing that I would like to propose that we do as a Rust project is that we should explicitly consider semver as part of the stabilization process for new features. I'll tell you why in a second. This is, broadly speaking, from a very high level, the feature lifecycle. Somebody has a brilliant idea, they write up an RFC, and then eventually it gets an unstable implementation in the Rust compiler. And there's a whole bunch of iteration that happens here. And then eventually, the feature is deemed good enough, we begin the stabilization process. We begin writing a stabilization report. And then we write a bunch of documentation explaining how this feature works, get diagnostics in order and everything like that. And then we stabilize. At no point at the moment is there a semver step in all of this. And I would like to add one. I think that we should insert an analysis of semver hazards as part of writing the stabilization report. This is important because it means that the person who is the absolute expert in that feature is helping find the edge cases that are notable and that are important to catch. That gives us more confidence that we nailed every single one of them, and it massively diminishes the amount of risk that we're facing in getting something wrong. If they thought about a semver hazard, they probably got all the edge cases right. I'm not very likely to, because I just read the docs and do the best that I can. And as part of thinking about what are the semver hazards in the report, we write documentation. Well, we should update the documentation because we have a page that lists all of the known semver hazards. Cargo has a reference, and we should add documentation on whatever we found in the stabilization report into that reference. This is good not just because now we have more complete documentation, it's actually good because now cargo semver checks can cite that documentation in explaining why the lint is there, why the breakage that we detected is actually breaking. So instead of us improvising with the diagnostic messages that we show to users in the few lines on the CLI that we have available for showing what is broken, we can direct them to a very well thought out piece of documentation with examples and explanations that will explain away any questions that they might have. That'll be a wonderful user experience. And if we can slip in these 2 extra steps into the process, then I think it'll be very, very likely that by the time the feature is stabilized, we should be able to have cargo semver checks lints available for that feature on day 1. And I think that would be awesome, because it is a glorious experience for users to know that they're protected while using that new feature from day 1. All right, so that closes the chapter of why we might not have known what the right rule is. How about not having the right data? Consider this example. Here we have a crate, and it just re-exports the API of another crate. And now we're making a change. We're just bumping the major version of that dependency, so we're re-exporting completely different items and types from the perspective of the Rust compiler. Obviously, major breaking change, right? This is not something that we can catch today, because we build the rust.json of the crate that we're analyzing. That rust.json says nothing changed. There was a re-export before, and there is a re-export now. So from our perspective, there is nothing to semver check here. No items have been changed, and so we're just going to say, no changes, you're good. That's a false negative. That's unfortunate. The problem here is that there's no reliable way for us to glue different rust.json files together. The rust.json output that we get just has insufficient information. We don't know how to connect things because there might be multiple major versions of a given crate that are available at any one given time, and we just don't know which one of them should be using. And because we don't have the right information in the rust.json, we just conservatively say, nothing to see here, we can't check this case, this is just a false negative. This is not an easy problem to solve. The reason it's still here, why I'm talking about it after 3 years of building cargo semver checks, is that if it were easy, we would have solved it. So it's a very challenging problem. And it actually requires a pretty complicated dance between rustc, cargo, and ruststock to get us all of the information that we need. It is necessarily a cross-team problem. It is not just RustDoc needs to do this one thing and then the problem is solved. And so you won't be at all surprised to hear that progress on this problem has been made one conference at a time. The last time that we met in person at Eurorust last year, we got in a room, we hashed out something that we thought would be decent, and moved on from there. I believe we're going to make more progress this time around, so I'm very happy that this is a longer conference as well. But that's actually not sufficient by itself. Solving cross-crate linking also causes more problems. Remember earlier how I said that building the RustDoc JSON for the crate that we're analyzing is 90 to 95% of the runtime? Well, if we build a lot more RustDoc JSONs, we're going to suffer really, really bad regressions in runtime. And if a tool is slow, then fewer people use it, which is just regrettable. So let's try to solve that problem as well. Let's try to avoid the performance cliff. One of the ways that we could do this is when we are linting this crate that re-exports something, we'll notice that the thing that is being re-exported, odds are, is actually in crates.io. It's a well-known version. And so if you ask, what are the items in this? What does the RustDoc JSON look like it? And when I ask for it, it's actually the same RustDoc JSON, so long as we're on the same platform, caveats apply. But more or less, they're the same items. We should be able to reuse the RustDoc JSON. Can we avoid rebuilding it? Can we just use a ready-made RustDoc JSON somehow? I hope so. Again, these are half-baked ideas. We're approaching it with the mindset of, let's see what would it take. And so one option is, DocsRS already builds RustDoc HTML. Can we get it to also build RustDoc JSON and just host it? And this is a half-baked idea for a variety of reasons, like the RustDoc JSON format keeps changing versions and so on and so on. But it's not a terrible idea, and I'm pretty sure that we can work out all of the edge cases if we decided to. Another option would be cargo publish is already verifying that your package builds, right? It's essentially doing a cargo check for you. Well, the cargo check portion is the expensive bit. The writing down the RustDoc JSON once you have everything you needed is not actually that expensive. Could we get cargo publish to build the RustDoc JSON and just upload it as part of crate metadata somewhere? Again, lots of things to work out. This is a half-baked idea. But I'm pretty sure that, again, if we sat down, we could probably figure out some way to get this to work. The point in showing you all of these examples is that I think that there is a solution in the solution space here, not to try to get us to get to any particular solution. I think it's a problem that's worth solving, and I think we can solve it. All right, so upstream broke Semver was one option. How about when we have a breaking but non-major change? In this case, Alice and Bob agreed that Bob did the right thing, right? Bob released a minor version because the change was not decided to be major by the, for example, API Evolution RFC. But that's not any consolation for Alice. She still ran cargo update, and she's still, holding the pieces of her broken project. So that's just unfortunate. An example of this is if we have, for example, a struct that wraps a string, and we have this asref implementation that lets us treat it like a string slice. So when we use it as a string slice, we do this asref call, and then we can do len on it as a normal string slice. Easy. Now we add another asref implementation to a byte slice, and all of a sudden, all hell breaks loose, because the compiler no longer knows what that asref call is talking about. And it will give us this helpful error message. It will say the type must be known at this point. Data.asref is the problem. And the suggestion says textblop as asref t is the thing that is confusing. So we need to make an explicit choice of which trait we're calling asref on. The specific problem here is that the compiler cannot figure out that t parameter in the middle. Everything else is fine, it's just that t that's the problem. But this also hints at the solution. The compiler was always doing this kind of rewriting under the hood. It always was figuring out what that t is. And in the previous version, this worked fine. So can we just figure out what t was in the previous version and go from there? Here's what I'm thinking. Imagine a future hypothetical cargo fix -- update tool. Or maybe it's a separate tool like cargo Semver checks. And it does something like this. If you ran cargo update and now your project is broken, it does a couple of things in order. First, it records all of the broken call sites. We already have this diagnostic information from Rusty. It's data.asref in that file and that line number. And then it rewinds the update. It goes back to the previous version that was known to build and asks inference, hey, what's that t thing in there? Oh, it's string. Okay, great, like stir slice. Perfect. Let's fill that in. it reapplies the update, and it fills in the inference result. It rewrites your code to use the explicit form with all of the type variables that were previously inferred. Okay, great. Let's see if that worked. We run cargo check. One of two things could happen. Either everything's fine, in which case, great, we solved the problem. Yay, no more breakage. Or we didn't solve the problem, but we're not really worse off than before. The project was broken to begin with, so we just undo all of the changes that we did, and we just throw up our hands and say, hey, user, sorry, you need to fix this. We can't do it for you. This is, again, not a full flow, and it will not solve every kind of inference breakage, but it will solve kind of a lot of them, I think. So the point of this is that we can 80-20 our way to problems being sort of arbitrarily small. I'm pretty confident that, just like with cargo sandwich checks, we can make inference breakage a lot less annoying by having tools like this. All right, so breaking but not major change out of the way. Is there a third option? As it turns out, there is, and it's perhaps the most unfortunate one of all. Alice and Bob disagree on what happened. There was a piece of the API that was maybe public. And that's really sad. Here's how that happens. Bob wrote this code. There's a public struct that has some fields and derives some traits, partial, ORed, serialized, deserialized, things like that. And in version 1.1, Bob shipped a tiny little change, just reordered the fields. But it's the same struct, right? It still has the same fields. It still derives the same traits. It's all good, right? Well, as it turns out, derive partial ORed derives the partial order in the order of the fields in the struct. And because we changed the order of the defined fields, we changed the sort order. Now, is that a problem? I don't know. Alice was using Bob's code. So she was generating some vector of data types, and she was sorting that vector and just persisting it to disk. And then later in the application, maybe loads it from disk and then does a binary search over it. It was sorted when we saved it to disk, so binary search should be fine. So one day, Alice goes through this flow, generates a bunch of data, sorts it, saves it to disk, and then runs cargo update. And after cargo update, she loads the data from disk, and all of a sudden, the binary search is broken. There's an item right there. She can see it in the serialized format on disk, and binary search says, sorry, that data is just not present. So this code is objectively broken, but whose fault is it? What happened? The problem is that the sort is wrong. It's sorted, but with the old ordering. It's not sorted according to the new definition. And so the thing that happened is maybe major change. Alice will go open a GitHub issue on Bob's repo and will say, hey, you broke the public API in v1.1. And Bob is like, I don't know what you're talking about. And Alice says, the sort order changed. And Bob says, sorry, that was never public API. We implemented partial ORed. We still implement partial ORed. We always promised there would be the ability to compare things, but we never promised a stable order. And now Alice is upset with Bob. Not only from her perspective is her project broken, Bob is refusing to take accountability for what happened. And that is a very, very reasonable thing to think. From Bob's perspective, he's an open source maintainer. He's not paid to do this. Alice was just using some crate that she found in Crates.io. And so his burnout intensifies. He probably thinks about going to retire to a mountaintop somewhere. So the question I want to ask you is, who was right? Because I sure don't know. This is the difficulty of this problem. This is a socio-technical problem, and the socio part is at least as hard as the technical part. And the best way to solve this is to just be more explicit up front. Now, we actually have concrete examples of Rust allowing us to opt out of API guarantees explicitly. Non-exhaustive is one of them, and I really love it. Target feature, which we talked about earlier, is also another one. Instead of a function being callable at any time, target feature might say, actually, you might not be allowed to call this function in certain contexts. So there is precedent for this kind of thing, and we just need to lean into it and add more of these kinds of features. What we want is explicit guarantees that are machine checkable. Here's an example of what that might look like in the concrete use case that we were just talking about. We might add an attribute that obviously needs a lot of workshopping, but this is what I'm calling it right now. Semver exclude stable order. Now we can determine which code was wrong. If you explicitly said, this is partial ORed, but it does not have a guaranteed stable order over time, then you cannot sort and then save to disk and then update and then reload from disk, right? Whenever you get a piece of data from disk, you cannot assume that it was sorted. You have to sort ahead of time. And if you didn't have this, then obviously that assumption was maybe fine, or we could decide this with in collaboration with the Lang team. They're specialists at this, and I'm not. And importantly, just like adding target feature and non-exhaustive, adding this after the fact to an existing type is a major breaking change, and that is something that we can lint with cargo semver checks. So not only are these more explicit guarantees helping users avoid these contentious situations where they're both pointing at each other and at deciding who is wrong, they're actually helping cargo semver checks prevent this kind of issue from happening in the first place. All right, so these are the three possible cases that we might be in. Upstream broke semver, there was a breaking but not major change, and the change was maybe major, and Hiram's law made somebody rely on something that they maybe shouldn't have. What I'm asking all of us to do is to have empathy for imperfection. None of us here is perfect. The semver study showed that. We all ship semver violations, and I will definitely throw myself under that bus because I've definitely done it. And the important thing to note here is that our users are imperfect as well. They make mistakes. They're impatient. They don't read the docs. They make bad assumptions. They rely on things that should not be relied upon. And the more we make Rust an accessible language to everyone, the more users we'll have and the more imperfection there will be. So this problem is not going to get better over time. It's going to get worse. So I'm asking us to remember that Rust leads by example with empathy. I think Rust is the most empathetic language, most empathetic programming language out there, but I don't think we should stop at that. I think we should keep making it even more empathetic over time. So hopefully by now I've convinced you that eradicating unintended breakage is not easy. It's actually a very, very, very hard problem. So this is not going to be a quick fix. But I think it's a problem that's worth solving. We need to have a user-centric view that's not centered on any component. This is not a compiler problem. This is not a Lang problem. This is a problem that affects our users and needs everyone's participation to be solved. We need a how can we do it attitude as opposed to it can't be done attitude in order to solve it. Because a lot of these problems are solvable, but we have to decide that we need to solve them. We need to carve out space and time for cross-team work, which is why I'm very grateful that we're having an all-hands attached to this conference. It's going to be super helpful. And we need to lean into idea sharing, having determination, and hopefully finding years worth of funding, because this problem is not going away this year or next year. This is maybe a Rust 2035 kind of thing if we actually want to eradicate it. But I do think it is a problem worth solving. I think we want to eradicate accidental breakage. And now that we know the way, I think we should say, let's get going.
Thank you very much. I think we have time for a couple of questions, if anybody has them. It's looking too high, sorry.
So you suggested that we'd have some way to specify that something doesn't have a specific guarantee, but there's also the opposite direction of, by default, not having guarantees and saying you specify more of them. Do you have opinions on that direction?
Not particularly. I have an opinion on having a default understanding of what is the, if nothing is specified, what is specified. I think this is more of a Lang team question. Cargo semver checks will just do whatever is right. A lot of the time we see these norms sort of come up in the ecosystem and then get sort of, happen the way that they came up. If we manage to get ahead of it and make a concrete choice, awesome.
All right, Nico.
Great talk. I'm all in on the big picture. I'm curious about something, which is you described sort of cargo fix -- update. I was wondering about cargo update without a -- fix. And also, in other words, part of updating your dependencies is fixing your code. I'm also curious about the idea of letting crate authors kind of annotate and specify how those updates should be done, right? Give hints to the compiler. Have you thought about that at all?
Absolutely. In fact, an earlier version of this of that slide said cargo update -- fix because I did not dare presume that we would want to, include my suggestion into mainline cargo update. If that's an option, that we're willing to pursue, I think it would be a fantastic idea. I also think that because cargo semver checks can generate lint reports on what changed, We might even be able to extend that and say, hey, actually, here's a code mod that is required by this change, right? So that we can make cargo update work across breaking changes as well, right? So we know what broke. This function takes an extra argument. Okay, it is required to have a code mod that fixes that. The default value of that argument is 0. Great. Rewrite the call site accordingly. That is also something that we can lint. Of course, the limiting factor here is time and funding. So all of these ideas are great, and I think they're absolutely doable. We should do them. The question is finding the time, space, and money.
I'm sorry to say that we are at time, so I know there's a few more questions. I'm sure that Predrag would be more than happy to talk with everyone about this. Thank you again to Predrag.
Please find me in the hallway after all of the talks are done. I'm more than happy to talk about this.
All right, next talk is in about 10 minutes. All right, it's time for our very last session of the Rust project track. I'm a little bit sad and emotional, but we'll get through this together. We have a couple of bonus speakers. I thought it was just going to be Nico, but we also have Jack Huey and Tim McNamara, and they're going to tell us all about the Rust Vision doc and you. All right, take it away.
All right. Is this on? Yeah, I think it is. Okay. Yeah, it's right. It was just going to be me, but this was much better, right? I think it's better. But the good news is we have not dry run this once, and we made it about an hour ago. So expect some roughness. That's the charm. It's going to be good. So we're talking about the Vision doc. What is the Vision doc? Probably many of you know, but maybe not everyone. The idea of the Vision doc is it's an effort that we're kicking off where we're trying to answer a kind of rather relevant question as we sit here at the 10-year anniversary of 1.0, which is, what should we be doing, actually? Many of the original goals for Rust, in some sense, were achieved. I think my personal one, when I first started, I was like, I'll be happy if somebody writes a Rust program and I don't know about it before it's done. Like the first time a library comes out that I haven't heard from the author as they're building it. That will probably never happen, but that would be really cool. We did pass that threshold at some point. And so, you know, what are we going to do now? What comes next? And this is something that I'm pretty excited about. And the reason is kind of three of them. The first one is I want us to start thinking beyond just adoption. Right? It used to be that kind of when Rust was small, adoption was like a priori good. Anything that would increase adoption was probably a good idea. I don't think that's true anymore. Right? We have to start asking ourselves, what should we be doing with Rust? We know we're going to be in a polyglot world. We don't expect everyone to rewrite everything in Rust, jokes aside. So like, how are we going to inhabit this world, and what space is Rust going to be targeting and optimizing for, and what space should we not worry as much about? That's one thing. Another thing is to help us stay focused. Our org has, like the Rust volunteer and, well, open source org, let's say, not only volunteers, has grown pretty large, right? We've got a lot of teams operating independently. It used to be we had a lot of teams, but half their membership was the same. So it kind of was, we were able to stay in sync pretty well, but more and more, I think that that's not true anymore, and that's a good thing. People are focusing, they're concentrating, getting more specialized, but it means that we can easily diverge and not share priorities and kind of have a different sets of facts based on our different perspectives, right? People maintaining the compiler have one set of things, people maintaining the language have another, and sometimes those come into conflict. So I'd like us to kind of get on the same page as much as we can. And the last one is to help have some conversations that I don't know how we're going to have otherwise. And what I mean by that, well, let me just step aside from my project role for a second and put on my Amazon hat and say, when I'm talking to people in Amazon, I hear a very different set of questions than the ones that come up like in an RFC thread or on internals. They're often much bigger than just a language design decision. They're more like ecosystem-wide, right? So I see people adopting Rust. I have some picture of what people are using it for. They're building network services. They're building out consumer devices. These are two very popular areas. There are other things. And I see that there's a really good argument. There's a really good reason people are adopting Rust, and it's mostly memory safety, right? So within Amazon, that actually let us use a lot of Java. Now, hey, we can use Rust instead, and we can have the same sort of productivity and memory safety wins while operating at a lower level, more efficient. That's awesome. But I also hear people being really concerned. Like, what's going to happen when the EU passes new regulation or some other place lifts new regulation that requires well-maintained crates in my supply chain? And when I look through my Rust dependencies, an awful lot of them have a single maintainer. And sort of by definition, that's not a well-maintained library per this law, right? It's not like, oh, you just don't know enough. It's actually legally required. Or what's going to happen when I have 0.1, 0.2, and 0.3 in my crate graph, and there's a CVE? How are we going to fix those things? So these are the kinds of concerns I'm hearing. And like I said, I don't know how we would talk about that, because the solution probably spans, some of it is in the project, but some of it is like, as an ecosystem, we need to take this seriously and get stuff to 1.0 and so on. And it's just not something we have a setup for. So the Vision doc is trying to fill that gap. So what are the things that we're looking
to do in this document. In some sense, answer questions. So the kind of questions come in maybe 2 chunks. There's sort of Rust the product, which is like, what is Rust's mission? Why is it here? What should it be doing? What are people using it for? What's working really well? What's working not so well? And what would unblock new areas where Rust would really bring a lot of benefit?
And the interesting thing about that is that it seems like a very, very technical response, right? It's like, these are the things of the language that we're really interested in developing, but that's kind of not the whole story.
Yeah, indeed. I forgot you were going to take this part. See? I was ready to go and, all right, carry it, Tim.
Yeah, no, just that, that the Rust project itself has got a series of like structures in terms of teams, working groups we've explored. There are, other mechanisms, and that's kind of got us to where we are. And we need to make sure that as a community, as a project, that the structures that we have in place are going to continue to let us go forward.
Yep. To scale up, because I think actually in Predrag's talk, I don't know how many times people have talked about burnout in this, but I've heard it more than once. It's definitely a theme. It's a concern. It's a concern of mine personally. It's a concern of all of us. But also, we have a lot of resources available, and maybe we can find better ways to deploy them. But we have to have the right conversations to make sure it goes right. So I see this personally as part of a kind of larger story of organization, trying to build out our sort of next generation organizational scheme within the project. The vision doc kind of is meant to give us the lay of the land. So I envision it saying things like, well, what you see there on the screen. Of the 22 people we spoke to, 18 care about C++ interops. Real hard data in some sense of what kind of things we heard and how often, but also giving the framing of why they care about it, what are they trying to do with it, and why does it matter? And as a result, maybe some suggestions of possible things we could do, but not much deeper than that. It's not going to tell you, there's a lot of different ways to do C++ interop. You can do CSX, you can do deep interop, and there's a bunch of space in between. So that's not really, that's a little too much for the vision doc, I think, but it should outline the kinds of problems that we need to solve in order to unlock things.
Yeah, and again, this is not just technical, right? We also want to know and think about how do we expand and let people across the entire world use Rust, right? So even people that today may not have good access or good adoption or exposure to Rust. So it's not just technical. It is also very much about people too.
And it's not just companies, I should add. I mean, I put that example because it's easy and fresh, but I think it's very much like you said, in different areas, the blockers are different. Like in Africa versus EU versus US versus Asia, there are different things that come of mind, right? And so I think this fits with some of what we have already, somewhat. So with the project goal system, where we've been establishing these 6-month goals, we have these kind of flagship goals, and you can imagine that they would derive somewhat from these, right? They're like, all right, we have this big thing, let's try to get more specific. How are we going to address interop? What percentage, what part of it? And then we have the project goals that are like the tactical steps of, okay, what are we going to do right now? How are we going to move that ball a little bit forward? Now, personally, I think this is good. It's still missing something, which is mainly the flagship goals are like, well, how do we decide those? Right now, let's be honest, right now it's Nico decides them because I'm running the program, but it's whoever runs the program kind of decides, right? And they're kind of obvious right now in some sense, but I think we need it to elaborate them and build a better understanding of what is that goal and are we all really aligned around it? So personally, I'm not going to go deep in this because this is like not really the point of this talk, but I just want to throw it out there. I think we need something in between to establish sort of the North Star that we're working towards in more detail, kind of lay out, like if we had done it for async Rust, we might have laid out, hey, these are some of the things we're trying to achieve with async Rust. I think we never wrote that down, at least in an RFC form, and formally decided it. There was a lot of understanding, but also a lot of different understandings, and it's sometimes become an obstacle later. So I think it'll be really valuable. I'm curious to talk to folks after if you have thoughts on that. But for this talk, we're focused on the vision doc. So let me talk you through the methodology, and then I'm going to start handing off to these folks to do more detailed stuff. We began by doing a survey, and the idea was basically just get a really broad picture of where we are at. And now we're in the process of looking at that survey, but also doing one-on-one interviews where we talk to people or companies for like 30 to 45 minutes and try to understand better what's going on there. After which comes this process, which I think is amusingly called coding. It has absolutely nothing to do with writing a program. It's like analyzing the data, figuring out what are the common trends you heard, what are the things that people told you, and what does that mean, right? And then finally oh, well, this is important actually. All of this work is very qualitative. We're kind of talking to people. It inherently can't tell us things like how common is that. You can kind of find out what themes are out there, what are the things that happen. And of course you may notice like, oh, literally every single person I talk to brings up the same thing. But nonetheless, I'm still talking to like 5 people or 10 people. There are more in this room, right? We're not than there are in our sample set. So that's where there is a sort of need to do quantitative assessments. So after you've gotten hypotheses, you've talked to people, you have some ideas, you have to go back out and validate those.
To be clear, it's 5 or 10 people per group, right? We're going to talk to a lot more than 5.
We've already talked to more than 5 or 10. But the point is, it's not like you can sample a significant portion of the Rust users in the world, right? It's just not possible. And that will take us to blindingly brilliant insights. That's our final stage, hopefully. All right, let me hand off to Jack, who's going to talk more about the survey.
All right, so last month now, we did a survey. Maybe some of you took it. It was, I think, a success.
You want that?
Thanks. Basically, we had 3 goals for it, which I don't remember what I wrote down. The first was to actually make sure that the groups and the ideas that we had thought about going into the survey, that we're actually sort of not missing something. And so, we'll talk about it in a second, but we actually maybe did miss a few things, but also I think we actually did pretty good. The second is we want to get sort of an idea of some common themes, right? So this is sort of similar to the first, but in the sort of freeform section, start to figure out what we're going to eventually do coding for. And when we do the interviews, start to think about maybe what questions we might want to ask and dig into. And then finally, we wanted to actually identify people that we could do interviews for. So we, in the project and within the Vision Doc team, specifically, we have some contacts and we know some people on who we might want to talk to, but we don't know a lot of people, and we definitely don't know everyone that we should be talking to.
Yeah. One more fine point on it. We don't just want to talk to our friends. that would be fun, but...
Yeah. So the survey has 3 sections. The first section is quantitative and demographic information. This is going to be most similar to the annual Rust survey, right, where it's not going to be freeform, and it's just to get a lay of the land in terms of putting the rest of the data on. The second is the freeform questions, which basically we ask some open-ended questions, which I'll show in a bit, and we let the people who answer the survey write what they want. And this certainly means that we get a lot of data and we have to go through it. Nico thinks some AI might help, but we'll see. And then the final section is contact info and referrals. So if somebody says, yeah, I'd like to be interviewed, they can give us their email. If they say, I actually know someone that you should talk to, we say, hopefully you know them in person and, it's a direct referral. But we got some good referrals from that. But overall, actually quite a good survey. So we ran this from April 4th through 28th, so basically a whole month, and ended up with quite a lot of responses. So almost 5,500 responses, and of these, little over a quarter, about a quarter, said, yes, if you want, you can come interview me, and I will give you all the information in the day. And this is awesome, actually. And in the survey, one of the things we ask for is, where are you located? And I wanted to say, surprisingly, I thought that there would be more of a closeness between Europe and the US, but Actually, more than half said Europe. Maybe not surprisingly, we didn't get a lot of representation from the Middle East and Latin America, but we did get some survey responses, and we can at least get a little bit of data.
It's probably obvious, but worth saying, there's no reason to think this means this is an accurate percentage of people who write Rust. So it's reflective of something, but I'm not sure what.
The other thing to mention is that any of these results are extremely formative. Like, we are like sort of just at the beginning stages of kind of like digging through, but
yeah.
Yeah, these are more or less at this point just raw stats, and really the key questions and the key insights are going to come later on whenever we've sort of identified common themes that we want to dig into. But this is, at the very least, a little interesting. And then, you know, for these quantitative questions, right, there are a few different ones, right? So one we asked is, how well do you know Rust? We asked, if you work for a company that you use Rust at, how big is it? And this was nice to see, right? So we essentially put 3 categories, small, medium, large, and got pretty good representation across them. And also a lot of people that didn't say they worked at a company that used Rust, but this could just be that they didn't want to answer or that they don't. So this is the comfort with Rust question. And there's actually sort of 2 points I want to highlight here. First is that we heavily skewed for people that are very comfortable with Rust, right? So if you see it just increases from 1 up.
Wait, are you telling me that people who answer a survey advertised on the Rust blog are more likely to be comfortable with Rust?
Yeah, and advertised by Rust people. Yeah, surely.
Yeah, so we kind of knew this going in, right? We kind of expected this.
So for those people who didn't go through the survey themselves, people were asked to self-select their own confidence level to language. So if you are 1, which is the lowest bar set of bars, the respondents were least comfortable with Rust, whereas we had lots of responses from people who are very confident with the language.
Yeah, and we tried to mitigate this by, you know, posting in places that might have people that are less familiar with the language, but ultimately, this is just sort of the data and how it
Now,
is.
we have a color code.
Yeah, so that was the second point that I was going to talk about.
Ah, cool.
Right? So the dark orange here, right, the dark Rust color, is all the people and what they say their comfort level is. But the lighter ones actually are the people that say that...
Gave contact info.
Yeah,
right?
that they gave contact info. And this is also maybe not too shocking, right? But the percentages are at the top. And you can see that the people who are more confident with Rust say, yeah, give me, you know, shoot me an email. Let me know if you want me to tell you more. And then the people that don't know Rust very well say, no, I'm okay. You know, you don't have to contact me. And this is a little bit of imposter syndrome, I think. And also, we often don't think that our opinion matters when we don't know a lot about it. And this is sometimes the case, right? But oftentimes, especially with this kind of thing, we want people's opinions, especially those who don't know Rust well.
And one of the things that...
The opposite. These people, they don't matter.
One of the things we don't really have information from are people who left Rust.
Yeah, that's a hard one. What?
I will also say that, I didn't put this in the slide, but going through this data, the people in the 1 category, a lot of them say they don't use Rust, right? So it's an interesting tidbit too.
One thing I want to say on this last point, I mean, I think all this stuff is interesting, and it's interesting the survey is skewed, and you might think that means that there's not a lot of value. I don't think that's quite true, because, as I said, the goal of this was actually as much to find people to talk to. So like the fact that we got 6.5% of ones saying they would like to talk to us actually means we have quite a lot of people we could talk to and learn about, hopefully get a sense of what things are occurring to people in those groups. Right? So it's kind of, we got enough representation from enough areas that's a good thing.
And you can also divide this out a little bit, right? So if you split out by number of people, or comfort level by region, this is, you know, mostly the same between regions, which is good. You could also say that, what is it, North America, US, seems a little bit more likely to say that they know Rust well, but again, it's hard.
The other thing to think about this is obviously we've normalized by region. And those regions which have fewer people, the thing that I found really interesting about this graph is that the shapes of that curve is relatively consistent even in much smaller communities.
Yeah. So then we have some questions that are less straightforward and maybe a little bit more clever in how you ask them. So we asked, if you don't use Rust, for projects that you haven't used Rust, what language would you have used instead? Or what have you used instead? The exact wording's up there. I don't know it off the top of my head. And, you know, there's responses, and we had a number of, you know, checkboxes that they could check, and they can check multiple. We also said only Rust, and we also had this other option which had some good answers. Maybe unsurprisingly, Python's top of the list. Go is down there, right? I won't talk too much about this, but there's some insights to be gained about that when you combine with other questions. But for the most part, we actually get in the survey pretty good coverage of people that use other languages and the types of languages that they use. The other question, right, the other thing we're interested in is, in Rust, what domains do you write for? Mostly CLIs, but again, this is checkboxes, so people can say, I wrote for a CLI app and I did networking, and that's actually really interesting because tangents.
So there's a correlation, obviously. People don't go into Rust typically just to do CLIs. If you want this is a correlation map, but it is duplicated, so it's mirrored, unfortunately. However, the thing to point out potentially is that if you're writing web services or backends, which is so-called cloud, then you like highly correlated to also write little developer utilities as well.
This dark square means a lot of people put both of those. So CLIs, and you probably can't read it, but it says cloud on the bottom.
And similarly, if you are into robotics, you're also into embedded. Like there's an overlap in a community. It's also interesting to note that there are a few whiter spots. So if you are writing native applications, you're less likely to be using writing, let's say JavaScript. No, you're less likely to just writing. If you're writing native applications, you're less likely to be writing native applications. Oh, did I just say that backwards?
You just said it. You said if you're writing native applications, you're less likely to write native applications.
Web APIs. Right. Goodness me.
All right.
I'm also suffering the end of day syndrome.
Yep.
And these are the freeform questions that we put, other than if there's anything else you'd like to tell us. But essentially, we put 3. I'll leave them up for like 2 seconds. I'm not going to read them. But more or less, for each question, we got about half the respondents that actually said something there. And if you read through them, some of them basically answered the same question in a different one. So this is going to require going through and reading and finding common themes, which
I think we have.
Which is coding. Let's, okay, cool. So this is what we are going to try to talk a little bit about how we're going through this process. So we read through, we're kind of pulling things out and identifying some themes. So let's go and push the right button.
Yeah, there you go.
Oh,
back one.
Okay, so here we have an example of, look, we asked them what was difficult to learn.
An actual comment.
This is an actual comment. The borrow checker is hard to learn. But there's a bunch of things. So we kind of need to unpack this. And so we start with 6 categories, and we're trying to put things into boxes. So what was hard, what was easy, because people are quite messy. They were answering different bits to different questions. And so we'd pull something out like this.
And we also, as we go, we're going to form new categories, right? So these were some, but there's going to be more.
Yeah, if we find a lot of comments that don't seem to fit.
So we found the borrow checker hard to learn, but we had lots of things that we really liked about the language. And then we can even start to take those sentences and push them into themes, essentially. Like, yeah, well, let's say the borrow checker or higher ranked trait bounds, we can actually associate some sort of weighting for how hard particular things are. Yeah. And with different levels of granularity. And the really valuable thing to do this qualitatively is that people can describe exactly how they feel, but they have different definitions about what things mean.
Yeah.
Oh, sorry. So sometimes it's kind of like unclear, or like we get like random stuff, or not random, but it's unexpected. So here's a longer response. Sorry, a longer.
I think this was Jack's.
I think so too.
All right. I don't know. Yeah, so this was...
You were saying you were surprised by this comment.
Oh, yeah. So one thing that was... I remember now. So one thing that when I was reading through some of the survey, and I found really unexpected, and Nico said he isn't surprised at all, was a lot of people say, I tried Rust, couldn't get it, walked away. Then I came back, and I tried it again, and it was, like, great. And this is... That was one example of this.
Yeah,
sorry. Oh, sorry. My apologies.
Yeah. But, one example of this, right, that I was worried I was going senile and gave Rust up. Several months later, I tried again with a different small problem and found it simple.
My favorite part is that they immediately resolved to switch all future development. So that's what I like to hear.
But this, there are
fantastic.
So many responses that say very, very similar things, and I was surprised. And there are other things, but this is just one example.
I was also very touched by people's generosity with their time, putting very, very thorough and thoughtful comments to essentially contribute to the project in their own way.
Like this one. It's great to have the detailed narrative. Yeah, so this is all just what we got on the survey, but what we're doing now is these deeper interviews, right? And we've been doing some while we're here, especially looking for, talking, I don't know how many have we done, 4 or 5, something like that, with some companies, with some other folks. And what the key thing when you're doing this, it's actually been an interesting learning experience. We had a UX researcher come and give us some of the little like tips of the trade, but the basic idea is you want to talk to people without biasing their results. So really letting them lead and following and asking questions, but not making suggestions or trying not to intimate what you think they should say too much. Anyway, I will point out, one of the reasons I'm talking to, or not all of us are talking to you, is that you might be interested to help. This is a novel and interesting way to work on Rust. So you can reach out to Jack and I or others if Jack and I are best as the 2 leads of this work, but if you might think you might like to do interviews or help us do coding and things like that, it can be pretty fun. It's also a little harder than you might think to not lead people on and tell them to say what you want them to say.
Surprisingly difficult.
Yeah. So where are we going next? I mean, we're going to do this coding, do this analysis, and figure out what kind of hypotheses we want to assess. And then we're going to have brilliant insights that will leave all of you astounded. That's what I expect to do. So I don't know where our timing's at, but I think we're doing all right. So the conclusion, is we're trying to get some insight into the state of Rust, and we're interested in getting help. So one thing I'll say is if you are at the all hands tomorrow morning, I want to do a dry run of the coding session, and what this means is Mara bought a ton of scissors, and I'm going to find a Kinko's or whatever the Dutch equivalent of Kinko's is, and we're going to print out copies of some of these transcripts and like cut them up. Like these are interesting sentences, and put them on boards, group them by categories. It's going to be very tactile, very fun, very not digital, and try to see what themes we start to see. And of course, you could also help by being an interviewer. We've kind of set things up so that people who are in the group are sort of self-leading, if you will, finding people to interview that you know and are in areas of your interest so that we can get as much coverage as possible. So that's a really cool thing to do. Yeah, that's about it. Anything else you all want to add?
If you think that you have an interesting case and you want to be interviewed.
Oh, that's a good point. That's another way to participate.
Yeah.
Definitely true.
The hardest thing we've found is getting people to believe that they are worth listening to.
That is true. And I guess I'll say what we're aiming to do is open an RFC eventually, saying sort of this is that people are aligned with this is an accurate representation of where we're at and what some of the priorities might be, and we all agree that they are important. Not necessarily picking the subset we're going to work on, but the pool of things that we see as critical next steps. All right, thanks a lot.
Thank you, all of you. We are on the clock a little bit for closing, but we might just have time for 1 or 2 questions if y'all are interested. Anybody got anything they'd like to ask? Okay.
Is there a way for folks to get copies of the data that you collected?
Good question. No, because we're trying to respect people's privacy. So we are limiting the data to people who are actively involved in the kind of analysis and so forth. So in general, we're being careful with that. But
We'll share. So the survey results directly we're not going to share, but we do plan on sharing like summary stats of the quantitative section, somewhat like we did today, but not just the raw data, but some deeper insights into it. We also may share quotes like this in the RFC, but yeah, the raw data is for privacy not going to be shared.
Yeah, what we told folks is we would share aggregate data and quotes, but try to avoid sharing the entirety or putting recordings or transcripts online for anyone to read, because that makes people a lot less willing to talk. That said, if you are active in the project or would like to get involved in the Vision Doc group, that's another way.
Okay, we've got time for 1 more, I hope.
Yeah, this will be a short one. Because Nico, you mentioned briefly that you are using some AI in this process, but later I heard you are using scissors.
We haven't used any AI actually, but we've got a lot of data to look through in a lot of categories, and I'm just kind of curious to know how effective it could be at summarizing and finding what things might match, which sentences might apply to which categories, so forth. But there's no substitute for reading it yourself. I think that's definitely true.
I, for one, do not want to give AI scissors, but as long as we don't cross those streams, I think we're okay. Thank you again, all 3 of you, for that. That was great.
Yep.
Let's give them a hand. All right, so we are at the end of the day. In a moment, we are going to ask you all to move to Cinema 12, but before that, I have a couple of just housekeeping announcements. Those of you who are attending workshops, the all hands, unconfs, and or the 10-year celebration tomorrow, and again, there are still tickets available for the 10-year celebration, that is not at this venue. If you come here tomorrow, you are only coming here to watch a movie, have fun. But if you actually want to attend those, you need to go to DUS, which stands for a series of Dutch words I will not attempt to pronounce. The Rust Week website, Rust Week is running buses out there from near here. The Rust Week website has the schedule, the pickup location, and so on and so forth, so please check that. There are drinks and a social tonight until 7 p.m. The cinema rooms need to be cleared by 6, I am told, because presumably the staff have to set it back up as a cinema. Thank you all for attending the Rust Project Track. This has been great. There's been just so many people here today, so many good questions, great talks, and it's been a pleasure having everyone here. The closing for the conference is going to be in Cinema 12, so those of you who would like to see that, please start shuffling towards the exit and head down to number 12. Thank you again.